You are listening to the Terraform Blueprint, building cloud infrastructure with infrastructure as code. Like and subscribe to keep up to date on our latest audiobooks. The Terraform Blueprint, building cloud infrastructure with infrastructure as code. Chapter 1, The Dawn of DevOps, understanding infrastructure as code. Introduction. From server racks to cloud control. Imagine a time not so long ago when setting up a new server meant ordering physical hardware, waiting for its delivery, meticulously racking it in a data center, connecting cables, and then installing operating systems and applications by hand. Even in the early days of virtual machines, provisioning still largely involved manual clicks in a graphical interface. Each step was a handshake, a command typed, a button pressed. This traditional approach, while once necessary, carried a hidden cost. It was slow, error-prone, and inconsistent. For businesses that needed to scale rapidly or adapt quickly to market demands, this model became a significant bottleneck. Today, the landscape of technology has shifted dramatically. The rise of cloud computing with giants like Amazon Web Services, AWS, Microsoft Azure, and Google Cloud Platform, GCP, has transformed infrastructure into a programmable, API-driven entity. No longer confined to physical hardware, our infrastructure, from servers and networks to databases and security policies, can be defined, deployed, and managed as easily as writing a piece of software. This paradigm shift is at the heart of what we call infrastructure as code, or ISC. This book will be your guide through this revolutionary approach to infrastructure management, specifically focusing on Terraform, one of the most powerful and widely adopted ISC tools available. Whether you're a seasoned IT professional looking to modernize your skills, a developer wanting to understand the infrastructure layer, or simply curious about how large-scale cloud environments are built and maintained, you've come to the right place. The problem with manual infrastructure, the snowflake server syndrome. To truly appreciate ISC, let's unpack the challenges inherent in traditional manual infrastructure provisioning. Inconsistency and snowflake servers. When infrastructure components are configured manually, even by the same person, slight variations inevitably creep in over time. One server might have a slightly different patch level, a forgotten configuration tweak, or an extra software package. These unique, undocumented configurations are often referred to as snowflake servers, because like snowflakes, no two are exactly alike. They are notoriously difficult to maintain, troubleshoot, and scale, leading to unpredictable behavior, and it worked on my machine scenarios across environments. Slow and error-prone deployments. Imagine setting up a complete production environment with dozens of servers, databases, load balancers, and networking rules, all by hand. It would take days, if not weeks. Each manual step introduces a potential for human error. A typo in an IP address, a forgotten firewall rule, an incorrect permission setting. These errors can lead to outages, security vulnerabilities, or simply wasted time in debugging. Lack of version control and auditability. Software developers have long relied on version control systems like Git to track changes, revert to previous versions, and collaborate effectively. Infrastructure, when managed manually, lacks this crucial capability. There's no clear history of who changed what, when, and why. This makes auditing for compliance a nightmare and recovering from accidental changes a high-stakes guessing game. Scalability challenges. As businesses grow, their infrastructure needs fluctuate. Manually scaling up or down in response to demand is a resource-intensive and often reactive process. It prevents rapid adaptation to traffic spikes or cost optimization during quiet periods. Difficulty in collaboration. In larger teams, coordinating manual infrastructure changes becomes a complex dance of communication and handoffs, often leading to conflicts and overwrites. These challenges highlight a fundamental truth. Manual infrastructure management doesn't scale, isn't reliable, and hinders innovation. It's like trying to build a skyscraper with a hammer and nails and no blueprints. Introducing Infrastructure as Code ISC, the blueprint for the cloud. Infrastructure as code is a revolutionary approach where you define your infrastructure configuration in a machine-readable format, such as simple text files. Instead of manually clicking through menus or running commands one by one, you describe the desired state of your infrastructure using a declarative language. This code is then used by an ISC tool to provision and manage your cloud resources automatically. Think of it this way: instead of drawing a house on a napkin and then telling individual contractors what to build, you provide a detailed architectural blueprint. Then, automation tools act as intelligent construction crews, interpreting that blueprint and building precisely what's specified every time. Core principles of ISC: declarative versus imperative. This is a crucial distinction. Imperative ISC, like using a shell script to run a sequence of commands, focuses on how to achieve a state, e.g., start server A, then install software B, then configure network C. If something changes, the script might not know how to adapt. Declarative ISC, like Terraform, focuses on what the desired end state should be, e.g., I want an EC2 instance of type T2 micro with this operating system. The tool figures out the necessary steps to reach that state, whether it's creating a new resource, updating an existing one, or doing nothing if the state matches. This makes it more resilient to changes and simpler to reason about. Idempotence, a key characteristic of declarative ISC. This means that applying the same configuration multiple times will always yield the same result, without causing unintended side effects. If a resource already exists and matches the desired state, the ISC tool will simply leave it alone. This predictability is vital for reliable automation. Version control. By representing infrastructure as code, you can store it in version control systems, like Git. This instantly provides change history, audit trails, the ability to revert to previous configurations, and facilitates team collaboration through techniques like pull requests and branching. Automation. ISC is inherently about automation. Once defined, your infrastructure can be deployed and updated consistently, quickly, and automatically. Collaboration. With infrastructure defined as code in a version control system, multiple team members can work on the same infrastructure definition simultaneously, using familiar software development workflows. Benefits of adopting ISC. Increased speed and agility. Provisioning complex environments shifts from weeks to minutes, enabling faster development cycles and quicker time to market. Consistency and reliability. Eliminates snowflake servers and configuration drift. Environments are identical across development, testing, and production, leading to fewer bugs and more predictable behavior. Cost savings. By enabling automated scaling, optimizing resource utilization, and preventing rogue resources, ISC can significantly reduce cloud expenditure. Improved security and compliance. Security configurations, firewall rules, IAM policies are codified and version controlled, making them auditable and consistently applied. Enhanced auditability and transparency. Every change to infrastructure is tracked in version control, providing a clear audit trail. Better quality software. When infrastructure is reliable and easily replicated, developers spend less time dealing with environment issues and more time building features. Why Terraform? Positioning in the ISC landscape. While many tools offer ISC capabilities, from cloud-specific options like AWS CloudFormation and Azure Resource Manager to configuration management tools like Ansible and Chef, Terraform stands out for several compelling reasons. Multi-cloud and cross-platform. Unlike cloud-specific ISC tools, Terraform is cloud-agnostic. It can manage infrastructure across AWS, Azure, GCP, VMware, Kubernetes, and hundreds of other services. This multi-cloud capability provides immense flexibility, preventing vendor lock-in and allowing organizations to leverage the best services from different providers. Declarative approach. As discussed, Terraform focuses on the desired end state, making configurations easier to understand and maintain compared to imperative scripts. Open source and extensible. Developed by HashiCorp, Terraform has a vibrant open source community. Its plugin-based architecture allows anyone to write providers to extend its capabilities to new services, making it incredibly versatile. Strong ecosystem. Terraform boasts a rich ecosystem of official and community-contributed providers, modules, reusable building blocks, and tools that enhance its functionality, from state management to policy enforcement. Industry adoption. Terraform has become a de facto standard for ISC, particularly in DevOps and cloud engineering roles globally. Its widespread adoption means a wealth of learning resources, community support, and a strong job market. In essence, Terraform acts as a universal translator for your infrastructure desires, speaking the native language of each cloud provider to manifest your blueprint in the digital realm. A glimpse into the journey ahead. Over the course of this book, you will embark on a structured journey to master Terraform. We'll start with the very basics: how to install Terraform and run your first infrastructure deployment. You'll then learn about the fundamental building blocks, providers, resources, and data sources, which are the core ingredients of any Terraform configuration. We'll move on to making your configurations intelligent and flexible using variables, outputs, and local values. A critical concept, Terraform's state, will be demystified, showing you how it acts as the bridge between your code and your actual cloud infrastructure. You'll discover how to create reusable components with modules and manage different environments with workspaces. As your skills grow, we'll delve into advanced techniques like conditional logic and loops to create truly dynamic infrastructure. Security is paramount, and we'll cover key best practices for securing infrastructure built with Terraform. We'll explore how Terraform seamlessly integrates into modern continuous integration and continuous delivery, CI/CD, pipelines for automated deployments. Real-world scenarios and common troubleshooting techniques will equip you for practical application. Finally, we'll discuss best practices, testing strategies, and chart a path for your continued learning in the ever-evolving world of ISC. By the end of this book, you won't just understand Terraform. You'll be able to confidently declare, provision, and manage your cloud infrastructure with precision, speed, and reliability. You'll be ready to bring the power of the blueprint to your cloud control. Recap and further reading. Infrastructure as code is not just a technological shift, it's a cultural one, transforming how organizations approach infrastructure management. By treating infrastructure as software, we gain the benefits of consistency, speed, and collaboration. Terraform stands as a leading tool in this revolution, offering a powerful, multi-cloud declarative approach. For further reading on ISC principles, search for articles and white papers on Phoenix servers versus Snowflake servers and immutable infrastructure. HashiCorp Learn, the official learning platform for Terraform, provides introductory concepts. Chapter 2, Unleashing Terraform, your gateway to automated infrastructure. Introduction. From concept to command line. In the previous chapter, we explored the transformative power of infrastructure as code and understood why Terraform stands out as a leading tool in this space. We learned that ISC treats your technology infrastructure like software, using code to define, provision, and manage resources. Now, it's time to roll up our sleeves and get our hands dirty. This chapter will walk you through setting up your environment, understanding Terraform's fundamental components, and performing your very first infrastructure deployment. The hello world of cloud resources. We'll focus on getting you comfortable with the essential Terraform workflow, initializing, planning, applying, and destroying your infrastructure. Terraform's architecture, a high-level view. Before we dive into installation, let's briefly understand how Terraform operates. It's surprisingly straightforward, built on a few core components that work together seamlessly. The Terraform Command Line Interface, CLI. This is the executable program you'll interact with directly. You'll enter commands like Terraform init or Terraform apply into your computer's terminal or command prompt. The CLI is the brain, coordinating all Terraform operations. Providers. Imagine you want to build a house, but you need specialists for the plumbing, electrical work, and framing. In Terraform, these specialists are providers. Providers are plugins that enable Terraform to communicate with various cloud platforms like Oz, Azure, Google Cloud, other software as a service, SaaS, offerings, or any system that exposes an application programming interface, or API. When your Terraform configuration asks for an AWS S3 bucket, the AWS Provider plugin knows exactly which API calls to make to Amazon services to create that bucket. The Terraform Registry, an online hub, houses hundreds of these providers for different services. Configuration files, HCL. You describe your desired infrastructure in plain text files using HashiCorp configuration language, or HCL. These files typically have a TF extension. HCL is designed to be human-readable and machine-friendly, making it easy to define your infrastructure declaratively. Meaning, you describe what you want, and Terraform figures out how to make it happen. State files. As Terraform deploys and manages your infrastructure, it keeps track of the actual state of your deployed resources in a state file. By default, a file named Terraform TF state. This file is critical because it's Terraform's memory, or source of truth, about what infrastructure it has created and currently manages. It maps the resources defined in your configuration to the real-world resources in your cloud account. This allows Terraform to know whether a resource needs to be created, updated, or deleted during subsequent operations. It's crucial that this file remains accurate and is not manually altered. This relationship, your HCL configuration defining your desires, the providers translating those desires into actions, and the state file tracking the real-world outcome, forms the foundation of Terraform's powerful capabilities. Setting up your environment. To get started with Terraform, you'll need the Terraform CLI and credentials to allow Terraform to interact with your chosen cloud provider. In this book, we will primarily use Amazon Web Services, AWS, for our examples, as it's a widely adopted cloud platform and its concepts are easily transferable to others. Installing Terraform. Availability. Terraform is a cross-platform tool, with binaries available for Windows, macOS, and Linux operating systems. Process. The simplest way to install Terraform is to download the appropriate package for your operating system directly from the official HashiCorp website. You can typically find it under the Downloads or Get Started sections for Terraform. Once downloaded, the package usually contains a single executable file named Terraform or Terraform.exe on Windows. Placement. To make Terraform accessible from any directory in your terminal, you need to copy this executable file into a directory that is included in your system's path environment variable. Common locations include /usr/local/bin on Linux and macOS, or a custom directory that you add to your path on Windows. Verification. After installation, open a new terminal or command prompt. Type Terraform version and press Enter. You should see the installed Terraform version number, confirming that the installation was successful and Terraform is accessible. Configuring Oz credentials. To allow Terraform to create resources in your AWS account, it needs authentication credentials. For development and testing on your local machine, the most common and recommended way is to use the AWS Command Line Interface, CLI, to configure your credentials. Install AWS CLI. If you don't already have it, first install the AWS CLI. Instructions for various operating systems are available in the official AWS documentation. Configure credentials. Once the AWS CLI is installed, open your terminal and run the command, Oz configure. The utility will prompt you for 4 pieces of information: AWS Access Key ID, a unique identifier for your programmatic access; Oz Secret Access Key, the secret key associated with your access key ID; default region name, the AWS region where you typically want to deploy resources, e.g., US East 1 for N Virginia, EU West 1 for Ireland. Default output format, you can usually leave this as JSON. Important security note: your access key ID and secret access key provide powerful programmatic access to your Oz account. Treat them with the same care as a password. For production deployments, team environments, or continuous integration systems, never embed these directly into your Terraform configurations. Instead, more secure methods like IAM roles for EC2 instances, OpenID Connect, OIDC, with CI/CD systems, or dedicated secrets management solutions should be used. For initial learning and personal exploration, Oz Configure is a convenient and acceptable method as it stores credentials securely on your local machine. Your first Terraform configuration. The Hello Cloud example. Now that your environment is set up, let's create a minimal Terraform configuration that defines a simple AWS S3 storage bucket. S3, or Simple Storage Service, is a popular cloud storage service used for everything from website hosting to backup solutions. Create a new directory for your project, for example, My First Terraform Project. Inside this new directory, create a new file named maintf. Now, open maintf with any plain text editor and conceptually add the following. Imagine the contents of maintf like this. This is a comment in HCL. Lines starting with hash are ignored by Terraform. The provider block configures the Oz Cloud provider. It tells Terraform we intend to manage resources within AWS. The region argument is essential for specifying where our resources will be created. Provider Oz. Region US East 1. Hash will start with the US East and Virginia region. The resource block declares an infrastructure component we want to create. OS3 bucket is the specific type for an S3 storage bucket in AWS. My First bucket is a logical name, like a nickname, for this resource within our configuration. Resource OS3 bucket, My First bucket. Hash bucket is an argument specific to S3 buckets, defining its unique name. This name must be globally unique across all Amazon S3 buckets, worldwide. Choose something distinctive to avoid conflicts, like your name and a random number. Bucket equals your unique bucket name. ACL, access control list, is another argument set to private for security. ACL equals private. Understanding the configuration, conceptual description, provider Oz. This block is your declaration of intent. It tells Terraform, hey, I'm going to be working with AWS resources. Inside its curly braces, you configure specific settings for the AWS provider, most importantly the region. The region equals US East 1 line instructs Terraform to create any Oz resources defined in this file within the AWS US East, Northern Virginia data center region. You can choose any region that is geographically or politically suitable for your needs. Resource OS3 bucket, My First bucket. This is the most fundamental building block in Terraform. It declares an infrastructure component you want Terraform to manage. OS3 bucket. This part is the resource type. It's a specific identifier that tells the Oz provider exactly what kind of Oz resource you wish to create, in this case, an S3 storage bucket. Terraform providers offer hundreds of these resource types, e.g., OS instance for a virtual server, Azure Virtual Network for a network in Azure. My First bucket. This is the local name or logical identifier you assign to this specific resource within your Terraform configuration file. It's like giving your S3 bucket a nickname within your code. Terraform uses this name to refer to this particular resource in its state file and when displaying execution plans. This name is only relevant inside your Terraform configuration. It doesn't automatically become the actual name of the resource in AWS itself. Inside the curly braces, here, you define the arguments or configuration parameters for the OS3 bucket resource. Bucket equals your unique bucket name. This is a crucial argument for an S3 bucket. It specifies the actual, globally unique name that the bucket will have in Oz. It is absolutely critical that the name you choose is unique across all S3 buckets created by anyone, anywhere in the world. If it's not unique, your deployment will fail. We've used a placeholder here, so remember to invent a truly unique name, perhaps incorporating a current date or a random string. ACL equals private. This argument sets the access control list for the bucket. While S3 buckets have many access options, setting it to private is a good security default, meaning only the account owner or explicitly granted users can access its contents. This simple maintf file declaratively defines your desired infrastructure. One private S3 bucket located in the US East 1 AWS region. Core Terraform workflow. Initialize, plan, apply, destroy. Now that you have your maintf file created, let's put Terraform into action. Open your terminal or command prompt, navigate to the directory where you saved maintf, e.g., cd My First Terraform Project, and follow these fundamental steps. Terraform init, initialize. Type the command, Terraform init. Purpose, this is the very first command you run in a new or cloned Terraform project. It sets up your working directory by performing several essential tasks. Most importantly, it downloads the necessary provider plugins specified in your configuration, in our case, the AWS provider, and configures the backend where Terraform will store its state file. What you'll see. The output will indicate that Terraform is downloading the AWS provider and successfully initializing the backend. You'll typically see a message like, Terraform has been successfully initialized. This also creates a hidden Terraform directory in your project, where the downloaded provider plugins reside. Analogy, think of Terraform init like setting up your workshop before starting a construction project. You're ensuring all your tools and blueprints are ready and in place. Terraform plan. Type the command, Terraform plan. Purpose. This is a critically important safety step. The plan command inspects your current Terraform configuration, compares it against the existing state of your real-world infrastructure, as recorded in the state file, or by querying the cloud provider if the state file is empty or outdated, and then generates an execution plan. This plan detailedly outlines what Terraform will do, which resources it will create, modify, or destroy, before it actually makes any changes to your cloud infrastructure. What you'll see. The output will be a detailed summary of the proposed changes. For our S3 bucket example, it will show something similar to Terraform will perform the following actions. #OSBucket myFirstBucket will be created. It will then list various attributes that will be set, such as ACL being private and showing the bucket name you specified. Finally, it provides a summary line like, plan, 1 to add, 0 to change, 0 to destroy. The plus sign, often described verbally as a plus sign in the output, clearly indicates a resource will be created. A tilde would indicate a modification to an existing resource, and a minus sign would indicate a resource to be destroyed. Analogy. This is your detailed blueprint review meeting. You're presented with exactly what will be built or changed before laying a single brick. Always run Terraform plan before Terraform apply. Terraform apply. Type the command, Terraform apply. Purpose. This command executes the actions proposed in the plan generated by Terraform plan. It interacts with the cloud provider's API to provision or modify the real-world infrastructure resources as defined in your configuration. What you'll see, Terraform will first display the same execution plan output that Terraform plan showed. Then, it will prompt you with, do you want to perform these actions? And ask you to confirm by typing yes and pressing enter. This manual confirmation is an additional safety measure. Upon confirmation, Terraform will proceed to create the S3 bucket in your AWS account. You'll see progress indicators in your terminal, and eventually, a message indicating apply complete. Resources, 1 added, 0 changed, 0 destroyed. Verification, you can now log into your AWS Management Console via your web browser and navigate to the S3 service. You should see your newly created bucket listed there with the unique name you chose. Analogy. This is when the actual construction work begins based on your approved blueprint. Terraform destroy. Type the command, Terraform destroy. Purpose. This command is the inverse of Terraform apply. It tears down and deletes all the infrastructure resources that are currently managed by your Terraform configuration as recorded in its state file. This is useful for cleaning up test environments or removing resources you no longer need. What you'll see, similar to Terraform plan and apply, it will first show you what it intends to destroy. The output will look something like, Terraform will perform the following actions. #OSBucket myFirstBucket will be destroyed. This means the S3 bucket named myFirstBucket will be removed. The summary will indicate, plan, 0 to add, 0 to change, 1 to destroy. You'll again be prompted to confirm with yes. After confirmation, Terraform will delete the S3 bucket from your AWS account. You'll see destroy complete. Resources, 0 added, 0 changed, 1 destroyed. Caution, Terraform destroy is an extremely powerful command. Always use it with great care, especially in shared or production environments, as it permanently removes resources. Ensure you are targeting the correct infrastructure before confirming. Analogy. This is like carefully dismantling the building, ensuring nothing unnecessary is left behind. This fundamental cycle of init, plan, apply, and destroy is the core rhythm of working with Terraform. You will repeat these commands countless times as you develop, test, and manage your infrastructure, growing from simple resources to complex architectures. Understanding Terraform's output. Throughout these commands, Terraform provides incredibly informative output. Always pay close attention to resource state changes. Remember the symbols plus tilde in the plan and apply output. They clearly indicate what action will be performed on each resource. This visual cue is vital for quickly understanding impending changes. Detailed attribute changes. Terraform lists specific attributes that will be set, updated, or removed for each resource, allowing for a precise understanding of the impact of an operation. Errors and warnings. If Terraform encounters a problem, e.g., a syntax error in your configuration, insufficient permissions to create a resource name conflict, it will provide an explicit error message. Read these messages carefully, as they often contain valuable clues for troubleshooting. Summary: the final lines of plan and apply, plan, X to add, Y to change, Z to destroy and apply complete. Resources: X added, Y changed, Z destroyed, offer a quick high-level overview of the operation's scope. Recap and further reading. You've just completed your first full Terraform workflow, from defining infrastructure as code to deploying and tearing it down. This foundational understanding of init, plan, apply, and destroy is the key to everything else you'll do with Terraform. You've also seen how providers connect Terraform to your cloud account, and how resource blocks are used to define specific cloud services. For detailed CLI command reference, explore the official HashiCorp Terraform documentation. Search for Terraform CLI commands. For more on HCL syntax and structure, review the HashiCorp configuration language, HCL documentation, which provides a deeper dive into the language used in your TF files. Chapter 3. The Building Blocks. Resources, Providers, and Data Sources Explained. Introduction. Deconstructing your infrastructure blueprint. In the previous chapter, we successfully deployed and managed our first AWS S3 bucket using Terraform. While that simple example provided a crucial hands-on start, it implicitly introduced essential components: the provider, the resource, and how Terraform accesses your cloud. This chapter will deconstruct these core building blocks, giving you a deeper understanding of their individual roles, their syntax within your configuration, and how they combine to form comprehensive infrastructure deployments. We'll also introduce a powerful concept called data sources, which allow Terraform to interact with existing infrastructure and integrate it into your new deployments. Providers. The bridge to your cloud infrastructure. As we touched upon earlier, Terraform itself is inherently cloud agnostic. It doesn't instinctively understand the intricate details of AWS, Azure, Google Cloud, or any other specific service's application programming interface, API. This deliberate design choice makes Terraform incredibly versatile, and it's where providers play their crucial role. What are providers? Providers are essentially specialized plugins that act as translators. They implement the logic for authenticating with and interacting with a specific service or platform. Each provider knows how to communicate with its respective service's API, how to translate your declarative Terraform configuration into the necessary API calls to create, read, update, or delete resources in that service, and how to represent the attributes of those cloud resources back within Terraform's state. Think of a provider as an expert contractor. Given a blueprint from the architect Terraform core, this contractor specializes in a particular trade, like electrical work, the AWS EC2 provider, or plumbing, the Oz RDS provider, and diligently executes the tasks within its domain in the real world. Declaring and configuring providers. You tell Terraform which external services you intend to interact with by declaring one or more provider blocks in your Terraform configuration files. These blocks typically include configuration arguments essential for that specific service, such as the cloud region to deploy into. Let's revisit our Oz example. Hash provider Oz block defines the Oz cloud provider. Hash, the region argument, is used to specify the geographical location where resources will be created. Provider Oz. Region US East 1. Other optional parameters can also be configured here. For example, hash profile equals my Oz profile, hash if you use named profiles in your Oz credentials file. Provider Oz. This specifies that we're opting to use the provider for Amazon Web Services. The Terraform registry houses myriad other providers. For instance, Azure for Azure, Google for Google Cloud Platform, Kubernetes for managing Kubernetes clusters, and even more specific ones like GitHub for managing GitHub repositories or Datadog for observability. Region, US East 1. This argument configures the Oz provider to operate specifically within the AWS US East and Virginia region. This is a common and usually required configuration for most cloud providers, ensuring your resources are deployed in a specific geographical location. Provider versions and constraints, required providers. Providers, like any software, are actively developed and updated by their maintainers. To ensure consistency across environments and to prevent unexpected behavior due to breaking changes in newer, incompatible versions, it's considered best practice to explicitly declare the required versions of your providers. You do this within a top-level Terraform block. The Terraform block is a special configuration block for Terraform itself. Terraform required providers specifies which providers this configuration needs. And from where they should be downloaded, source. Required providers. Oz. Source equals /Oz. Version 5.0. This tilde with greater than means. Any version equal to or greater than 5.0.0, but less than 6.0.0. It ensures backward compatibility within a major version. Required version specifies the minimum compatible version of the Terraform CLI. Required version equals 1.0.0. This means Terraform CLI version must be 1.0.0 or newer. The actual provider configuration block follows this. Provider Oz. Region US East 1. The source attribute within required providers tells Terraform where to find the provider. Usually /Oz refers to the official Oz provider on the HashiCorp registry. The version attribute pins it to a compatible range, often using a specific operator like ~, to allow for minor version updates while avoiding major, potentially breaking, changes. The Terraform init command uses these constraints to download the correct provider version for your project. Multiple provider configurations. In more complex scenarios, you might need to manage resources in different regions or even across different Oz accounts within a single Terraform configuration. Terraform supports this by allowing you to define multiple instances of the same provider using the alias argument. Define a primary Oz provider for the US East region. Provider Oz. Region US East 1. Alias primary. This is a logical name for this specific provider instance. Define a secondary Oz provider for the EU West region. Provider Oz. Region EU West 1. Alias Ireland. A different logical name for a different region instance. You could also specify different credentials here, e.g., for a different Oz account. Using the profile argument to reference a specific Oz CLI profile. When defining resources, you would then explicitly tell Terraform which provider instance to use. This S3 bucket will be created in US East 1. Resource, OS3 bucket, mybuckets. Provider equals Oz primary explicitly uses the provider with alias primary. Bucket equals US East 1 unique bucket name. This S3 bucket will be created in EU West 1. Resource, OS3 bucket, mybucketu. Provider equals Oz Ireland explicitly uses the provider with alias Ireland. Bucket equals EU West 1 unique bucket name. This mechanism provides fine-grained control over where your resources are deployed, facilitating multi-region or multi-account deployments from a single codebase. Resources. Defining your infrastructure components. Resource blocks are the concrete definitions of the infrastructure components you want Terraform to create, manage, and ultimately destroy. They are the most common and visible parts of any Terraform configuration. Each resource block corresponds to one or more real-world infrastructure objects like a virtual machine, a database, a network, a firewall rule, or even a serverless function. Syntax revisited. The general syntax for a resource block is resource, providrtyp, localname. Let's break down a more complex example, defining an Oz EC2 instance, which is a virtual server instance in the cloud. Hash this resource block declares an Amazon EC2 instance. Resource Os instance, web server. Hash AMI specifies the Amazon machine image ID to use. This is like a template for the OS. Hash this example ID would typically point to an Ubuntu server image. AMI equals AMI 0 updef 1,230 4,567,890. Hash instance type determines the virtual hardware specifications, CPU, RAM. Hash T2 micro is a small, often free-tier eligible instance type, good for testing. Instance type equals T2 micro. Hash tags are key value pairs used for organizing, identifying, and managing resources within AWS. Tags, name equals myappwebserver. Environment equals development. Hash other arguments like VPC security groupids, subnetted, keyname. Hash would typically be included here to specify network, security, and access settings. Os instance, this is the resource type. It's a specific identifier defined by the Oz provider, indicating that you want to create an EC2 instance. Terraform providers expose a vast array of these types, covering nearly every service offered by the cloud provider. Web server, this is the local name you assign to this specific resource within your Terraform configuration. This name is an internal reference. If you need to refer to specifically this EC2 instance later in your configuration, e.g., to output its public IP address, you would use Os instance web server. This local name only exists within your Terraform code and its state file. It doesn't directly become the actual name of the resource in AWS unless you explicitly set it, often via a name tag as shown in the example. Arguments, AMI, instance type, tags. These are the input parameters that configure the specific details of the resource. For an EC2 instance, you must provide at least an AMI Amazon machine image, which is essentially the operating system and pre-installed software template, and an instance type, which defines the compute and memory capacity. Tags, a very common and important argument across many cloud resources. Tags are key value pairs that help you organize, categorize, search for, and manage your cloud resources. They are invaluable for cost allocation, automation, and security policies. Here, we're tagging our server with name and environment to make it easily identifiable. Computed attributes. When a resource is instantiated in the cloud provider assigns it various attributes. For instance, an EC2 instance will get a unique ID, a public IP address, if requested, a private IP address, and a DNS name. Terraform captures these computed attributes after the resource is created and stores them in its state file. While you explicitly define AMI and instance type, these are arguments you provide, Terraform will learn the publicip or ID, these are computed attributes, after the resource is successfully provisioned. You can then reference these computed attributes in other parts of your configuration or as outputs for users. For example, Os instance web server publicip would give you the public IP address of the server once it's deployed. Lifecycle of a resource. When you execute Terraform apply, Terraform performs a create, read, update, or delete CRUD operation on each resource based on its comparison of your configuration and the current state. Create. If a resource defined in your configuration does not exist in the real world, as determined by the state file, Terraform will create it. Read. Terraform reads the current state of a resource from the cloud provider's API. This is crucial for detecting drift, where manual changes might have occurred outside of Terraform. Update. If a resource exists, but its attributes in the real world don't match your desired configuration, Terraform will update it. This might involve modifying existing attributes or even recreating the resource if an attribute change requires it, e.g., changing the instance type of an EC2 instance often requires recreation. Delete. If a resource is removed from your Terraform configuration, or if you run the Terraform destroy command, Terraform will delete that resource from the cloud. Understanding this CRUD lifecycle is key to managing infrastructure changes effectively and predictably. Data sources, querying existing infrastructure. While resource blocks are primarily for creating and managing infrastructure components that Terraform is responsible for, data sources serve a different, yet equally vital, purpose. They are used for reading information about existing infrastructure or external services without managing them. Why use data sources? Data sources allow your Terraform configuration to be dynamic and adaptable. They enable you to fetch information about resources that were provisioned manually or by a different team process, are inherently dynamic, like the latest version of an operating system image. Are shared resources across multiple Terraform configurations, are simply needed for reference to build other resources. Common use cases for data sources include retrieving the latest Amazon machine image, AMI, ID for a specific operating system, which frequently updates. Discovering details of an existing virtual private cloud, VPC, or specific subnet IDS, which you might rely on but not manage directly with the current Terraform code. Getting a list of available AWS availability zones for a given region to ensure even distribution of resources. Syntax. The syntax for a data source block is data, providrtyp, localname. It looks deliberately similar to a resource block, but the keyword data clearly distinguishes its intent. Example. Let's refactor our EC2 instance example to dynamically fetch the latest Ubuntu server AMI ID in us East1. AMI IDs are updated frequently, so hard-coding them, as we did previously, is a bad practice. Hash this data source finds the most recent Ubuntu server AMI. Data Asami, Ubuntu. Hash this argument ensures we always get the newest image. Most recent equals true. Hash this is the Oz account ID for Canonical, the publishers of Ubuntu AMIs. Owners equals 99,720,109,477. Hash filters to narrow down the search for the specific Ubuntu version. Filter, name is name. Values equals ubuntu/images/hvmssd/ubuntu jammy 22.0 4AMD 64 server. Filter, name equals virtualization type. Values equals HVM. Hash now, we create our EC2 instance, referencing the ID from the data source. Hash this ensures our EC2 instance always uses the current latest Ubuntu image found by the data source. Resource, OS instance, web server. AMI equals data Asami Ubuntu ID hash, referencing the id attribute from the Ubuntu data source instance. Instance set type equals T2 micro. Tags, name equals dynamic web server. Data Asami, Ubuntu. This declares a data source of type Asami and gives it the local name Ubuntu. Most recent equals true. This ensures Terraform actively searches for the newest image matching your criteria. Owners specifies the Oz account ID that published the AMIs. Canonical is the publisher of Ubuntu. Filter. A block that allows you to specify criteria, like name patterns or virtualization type, to narrow down the search and precisely identify the desired AMI. Data Asami Ubuntu ID. This is how you reference the output from a data source. Here, we're accessing the id attribute, which is the actual AMI ID from the Ubuntu data source instance. This dynamic lookup means your EC2 instance will always be created with the latest available Ubuntu image without you needing to update the AMI ID manually in your code. Distinguishing from resources. The crucial distinction to remember is this. Resource blocks are for infrastructure that Terraform creates and manages. Data blocks are for infrastructure or information that Terraform reads from the cloud. A data source operation will never show up as a create, update, or destroy action in a Terraform plan because it simply fetches existing information without modifying it. Dependencies in Terraform. Terraform is intelligent enough to understand relationships between resources. When you reference an attribute of one resource in another, e.g., using the ID of a newly created security group in an EC2 instance configuration, Terraform automatically infers an implicit dependency. This means Terraform knows it must create the security group before attempting to create the EC2 instance. because the instance depends on the security group being present. However, there are rare cases where Terraform might not be able to infer a dependency automatically, even if one logically exists. For such scenarios, you can use the depensen meta-argument to define an explicit dependency. For example, if you have a custom automation, like an Oz Lambda function, that needs to run only after a specific database is fully provisioned and ready to accept connections, you might use depensen. Define an AWS Relational Database Service (RDS) instance. Resource OSP instance, myApplicationDB. Hash. Database configuration details, instance type, storage, etc. Engine MySQL. Engine version equals 8.0. Instance eclas equals dbt, micro. Allocated storage equals 20. DB name equals app database. Username equals administer. Password very secure password. Hash in real scenarios, use secrets management. Skip final snapshot equals true. Define an Oz Lambda function that performs post-database creation setup. Resource Lambda function, database setup function. Hash. Lambda function configuration details, runtime, handler, code, role, etc. Function name equals database setup. Hash other Lambda configurations. Hash this depensen explicitly tells Terraform that this Lambda function should hash only be created and deployed after the myApplicationDB resource is fully provisioned. Depensen equals OSP instance myApplicationDB. While depensen can be useful, use it sparingly and as a last resort. Terraform's implicit dependency resolution is generally robust and preferred. Overusing depensen can make your configurations harder to read, maintain, and can sometimes obscure true logical dependencies, potentially leading to hard-to-debug issues. If you find yourself frequently reaching for depends on, it's a good opportunity to review and potentially refactor your configuration to leverage implicit dependencies, or to break down your infrastructure into smaller, more logically independent modules. Recap and further reading. You now have a solid understanding of the fundamental components of any Terraform configuration. Providers connect Terraform to the outside world, enabling it to speak the language of various cloud services. Resources are your direct instructions to Terraform to create and manage specific infrastructure components. Data sources provide a mechanism to query and integrate information about existing resources into your deployments, making your configurations more dynamic and powerful. By combining these building blocks with an awareness of dependencies, you can craft sophisticated and reliable infrastructure blueprints. For a comprehensive list of all available providers, resource types, and data sources, the Terraform registry is your primary and most valuable resource. You can search directly for specific services and find detailed documentation for each available resource and data source. For detailed conceptual explanations of HCL syntax and arguments, refer to the Terraform language documentation on the HashiCorp developer website, developer.hashicorp.com/terraform/language. Chapter 4, Smart Configurations, Harnessing Variables, Outputs, and Local Values. Introduction, the need for flexibility. In the previous chapters, we learned how to define and deploy static infrastructure using providers and resources. We created an S3 bucket with a specific name and discussed an EC2 instance with a fixed AMI and instance type. While this is a great start, real-world infrastructure is rarely static. You'll often need to deploy the same type of infrastructure, perhaps a web server, a database, or an entire application stack, multiple times, but with slight variations. You might need different instance sizes for development versus production environments, or different network configurations for staging versus testing. If you hardcode every detail into your Terraform configuration, you'd end up copying and pasting large sections of code, making maintenance a nightmare and increasing the risk of errors. Just as functions in programming languages allow you to encapsulate reusable logic with customizable inputs, Terraform offers mechanisms to make your infrastructure configurations flexible and reusable. This chapter introduces 3 powerful concepts: input variables, output values, and local values. Together, these features enable you to parameterize your deployments, extract useful information, and simplify complex expressions transforming your static blueprints into dynamic, adaptable templates. Input variables, parameterizing your deployments. Imagine building a house where you want to offer different options for the number of bedrooms, the type of roofing, or the color of the paint. Instead of drawing a new blueprint for every single variation, you'd create one master blueprint with placeholders for these customizable features. In Terraform, input variables serve this exact purpose. They allow you to define parameters for your configurations, making them reusable and adaptable to different scenarios without modifying the core code. What are input variables? An input variable acts as a named placeholder that can accept a value when your Terraform configuration is executed. It allows you to customize aspects of your infrastructure, like names, sizes, regions, counts, without directly editing the resource definitions. Why use input variables? Reusability. Deploy the same application stack across different environments, development, staging, production, by simply changing variable values. Customization. Allow users of your configurations, or modules, which we'll cover later, to easily adjust resource properties without needing to understand the underlying HCL. Maintainability. Avoid hard-coding values that might change, making updates easier and less error-prone. Clarity. Variables with descriptive names can improve the readability of your configuration. Declaring variables. You declare a variable using a variable block. For example, to define a variable for the AWS region, you might declare a region variable with a variable keyword, followed by the variable's name, for example, OSRegion enclosed in double quotes. Inside the block for this variable, you can specify various attributes. Description. This is a human-readable string explaining the variable's purpose. This is highly recommended for clarity and documentation. For OSRegion, it might state, the AWS region where resources will be deployed. Type. This specifies the data type of the variable's value. Common types include string for text, number for integers or decimals, bool for true-false, list for ordered collections of values, map for key-value pairs, object, tuple, and set. Specifying a type is crucial for validating input and preventing type mismatches. For our region example, the type would be string. Default. This is an optional default value. If a variable has a default, you don't have to provide a value for it when running Terraform. It will use the default. If no default is specified, the variable is considered required, and Terraform will prompt you for a value if it's not provided otherwise. For our region, you might set a default like US-East1. Validation. Introduced in newer versions of Terraform, this allows you to define custom validation rules for input variables, ensuring that provided values meet specific criteria, e.g., a regex pattern for a name, a minimum-maximum value. Sensitive. If set to true, Terraform will hide the variable's value in its plan and apply outputs, preventing sensitive information, like passwords, from being displayed in logs. So, a conceptual declaration for an OSRegion variable might look like this. A variable named OSRegion, with a type of string, a description of the AWS region where resources will be deployed, and a default value of US-East1. Providing values for variables. Terraform offers several ways to provide values for variables in order of precedence. Later methods override earlier ones. Command line, var. You can pass values directly when running Terraform plan or Terraform apply using the var flag. For example, Terraform apply var equals OSRegion equals US-West2. Variable definition files, TF-vars. For multiple variables or more complex values, you can create files ending in TF-vars or Terraform TF-vars. Terraform automatically loads values from Terraform TF-vars and Terraform TF-vars JSON in the current directory. You can also specify other TF-vars files using the varfile flag, e.g., Terraform apply varfile equals dev TF-vars. Environment variables, TF-var. Terraform checks for environment variables prefixed with TF-var. For example, setting an environment variable TFVA OSRegion equals EU-West1 will pass EU-West1 as the value for the OSRegion variable. From Terraform Cloud Enterprise, when using HashiCorp's managed services, you can define variables directly within the web interface, which is a common and secure practice for team environments. Interactive prompt. If a required variable has no default and no value is provided by any of the above methods, Terraform will prompt you to enter the value in the terminal. Using variables in configurations. Once declared and assigned a value, you reference a variable within your configuration using the var prefix, followed by the variable's name. For example, var osregion would give you the value assigned to the osregion variable. You could then use this variable in your provider block. Inside the provider os block, setting the region attribute to var osregion. Similarly, if you had a variable for an instance settype, you would set the instance settype attribute of an osinstance resource to var.instance settype. This allows you to easily change the region or instance type without touching the resource definition itself. Output values, exposing critical information. While input variables allow you to customize your deployments, output values allow you to export information about your deployed infrastructure. This is incredibly useful for several reasons, such as providing dynamic data to a user, passing information to other Terraform configurations, or integrating with continuous integration, continuous delivery. CI/CD pipelines. What are output values? An output value specifies an expression whose value will be displayed to the user when Terraform apply completes, and it can also become available when the configuration is used as a module. Why use output values? User feedback. Display important information like the public IP address of a newly deployed web server, a database endpoint, or the URL of a provisioned S3 bucket. Cross-configuration references. If you have multiple Terraform configurations, e.g., one for networking, another for applications, outputs allow you to pass resource attributes, like a VPC ID, from one configuration to another. CI/CD integration. CI/CD pipelines can consume Terraform outputs to perform subsequent steps, e.g., run tests against a deployed endpoint, update a DNS record. Declaring outputs. You declare an output value using an output block. For example, to output the public IP address of an EC2 instance, you declare an output with the output keyword, followed by its name, for example, web server publicip, in double quotes. Inside this block, you specify description, a human-readable text explaining what the output represents. For our example, the public IP address of the deployed web server. Value, this is the core of the output. It's an expression that evaluates to the data you want to export. This often refers to an attribute of a resource. For our web server, it would be osinstance web server publicip, referencing the publicip attribute of the osinstance resource named web server. Sensitive, if set to true, the output's value will be hidden from the CLI output and stored with extra care in the state, preventing sensitive data from being easily viewed. So, an output block to get the web server's public IP would look conceptually like this. An output named web server publicip, with its value set to the public IP attribute of the OS instance named web server and a relevant description. Accessing outputs. After a successful Terraform apply, the output values are displayed in the terminal. You can also retrieve them at any time using the Terraform output command, optionally specifying the name of the output you want, e.g., Terraform output web server publicip. Local values, simplifying complex expressions. Sometimes, within a single Terraform configuration, you might find yourself repeating complex expressions or calculations across multiple resource properties. This can make your code harder to read, maintain, and prone to errors if you need to change the logic in several places. Local values, often called locals for short, solve this problem by allowing you to assign a name to an expression, making it reusable within your configuration. What are local values? A local value is effectively a named constant or an alias for an expression within a single Terraform module, which is the current working directory, or a separate folder for reusable components. They are meant for internal use within your current configuration to improve readability and avoid repetition. They are not exposed as inputs or outputs to other parts of your Terraform setup. Why use local values? Avoid repetition, don't repeat yourself. Define a complex string concatenation or a calculated value once, and then reference it by its local variable name. Improve readability. Break down complex expressions into smaller, named components, making your configuration easier to understand. Centralize logic. If a specific piece of logic is used in multiple places, defining it as a local value ensures consistency and simplifies future modifications. Declaring locals. You declare local values within a locals block. You can have multiple locals blocks in your configuration, and Terraform will combine them. For example, imagine you want to consistently name your resources based on an environment and project name. You start with the keyword locals, followed by a block. Inside this block, you define key value pairs. For example, a key named project name with a value of Terraform blueprints, and a key named environment with a value of dev. Then you could have another key named common tags, and its value would be a map, for example, containing a project key mapped to local.projectName and an environment key mapped to local environment. This way, local.common tags would be a convenient map of tags you could apply to many of your resources. A more complex example might be creating a unique prefix for a resource name by combining variables. Let's say local resource prefix could be defined as var.projectcode$var environment. This would combine a project code variable and an environment variable with a hyphen. Using locals, you reference a local value using the local prefix, followed by its name. Continuing the example above, if you had a resource for an S3 bucket, you could set its bucket argument using the local resource prefix combined with a specific bucket purpose, like local resource prefix application logs bucket. This allows you to construct consistent naming conventions or attribute sets throughout your configuration without rewriting the same logic repeatedly. Combining them all. A dynamic web server example. Let's tie these concepts together with a slightly more elaborate example. Imagine you want to deploy a web server where the deployment environment, dev, staging, prod, and project name are provided as input. A consistent naming prefix for resources is automatically generated. The public IP address of the deployed server is easily accessible upon completion. Input variables, variables TF. You would define variables for environment, e.g., string type, no default, and project name, e.g., string type, default, my web app. Local values, locals TF. You would have a local value, like local resource prefix, set to var.projectName$var environment, creating a string such as my web app dev. You could also have local.common tags as a map, including project and env tags derived from var.projectName and var environment. Resource configuration, main TF. Your EC2 instance, an OS instance resource, would use these locals and variables. Its instance settype could be a variable, e.g., var.instanceSetType, allowing different sizes per environment. Its tags could be set to local.common tags, ensuring consistency. Its name, via a name tag within tags, could be local resource prefix web server. Output values, outputs DF. An output named web server accessip would be defined, with value equals OS instance web server publicip and description equals the public IP address to access the web server. When you run Terraform apply, you could specify var equals environment equals prod, var equals instance settype equals T3, medium, and Terraform would use prod and T3 medium for variables. Calculate local resource prefix as mywebappprod. Deploy a T3 medium EC2 instance named mywebappprod web server with correct tags. Output the public IP address for you to access. This demonstrates the power of combining these concepts to create robust, flexible, and easily manageable infrastructure definitions. Recap and further reading. Input variables are your way to customize Terraform configurations, making them flexible and reusable for different environments or contexts. Output values provide a clean way to expose important information about your deployed infrastructure to users or other systems. Local values simplify complex expressions and improve the readability and maintainability of your configuration by preventing repetition. Mastering these three concepts is fundamental to writing effective and scalable infrastructure as code with Terraform. They allow you to transform a rigid blueprint into a dynamic template that can be adapted with ease. For detailed information on supported types, validations, and variable loading order, Consult the official Terraform language documentation on input variables. For more on outputs and how they are used, especially with modules, refer to the Terraform language documentation on output values. For advanced examples and use cases for local values, look into the Terraform language documentation for local values, particularly the sections on complex object construction. Chapter 5, The Heart of Terraform, Mastering State Management. Introduction, Terraform's memory and source of truth. In the preceding chapters, we learned how to declare our desired cloud infrastructure using Terraform's configuration language, and we executed commands like Terraform plan and Terraform apply to bring our blueprints to life. But how exactly does Terraform know what resources already exist in your cloud account? How does it figure out what needs to be created, updated, or deleted during an apply operation? The answer lies in a crucial, often misunderstood component, the Terraform state file. The state file is the literal heart of Terraform. It's Terraform's memory, its source of truth, and the critical link between your beautifully crafted configuration code and the complex reality of your deployed infrastructure in the cloud. Understanding how Terraform manages its state is not just important, it's absolutely essential for effective and safe collaboration in any real-world environment. What is the Terraform state file? At its core, the Terraform state file is a JSON, JavaScript object notation, formatted file that maps resource definitions in your Terraform configuration to the actual real-world infrastructure resources that Terraform has provisioned. It's a precise inventory of every resource Terraform manages, including their unique cloud IDs, their current attributes, and important metadata about how they relate to your configuration. Purpose: mapping. It acts as a bridge, understanding which OS3 bucket resource block in your code corresponds to which actual S3 bucket deployed in AWS. Tracking. It records the current values of all attributes for managed resources, including those computed by the cloud provider, like a public IP address or a resource ID. Performance. By knowing the current state, Terraform can efficiently compare it with your desired configuration during a Terraform plan, determining exactly what changes are needed without having to requery the cloud for every resource every time. Dependency management. Though Terraform often infers dependencies from references, the state file implicitly helps Terraform understand the relationships between resources it has deployed, ensuring resources are created or destroyed in the correct order. Why you must not edit it manually. The most important rule about the Terraform state file is this: never manually modify Terraform TF state or any state file with a text editor. It's like manually rewriting a database during a crucial operation. The state file is a precise, machine-managed record. Any inconsistencies you introduce can lead to state corruption. Terraform might lose track of resources, leading to orphaned infrastructure in your cloud account that it can no longer manage. Data loss. Terraform might attempt to recreate resources it thinks are missing, potentially overwriting existing, critical infrastructure. Inaccurate plans. Your Terraform plan will no longer accurately reflect the changes that would occur, making it unreliable. Race conditions. In a team environment, manual changes can lead to conflicting updates and further corruption. Always use Terraform commands to interact with the state, e.g., Terraform state MV for moving resources, Terraform import for bringing existing resources under Terraform management. Analogy. Imagine the state file as a meticulous, real-time inventory list for a complex factory maintained by a robotic system. It knows exactly where every machine, every part, and every product is. If a human manually scribbles changes on this list without telling the robot's next operation will be based on faulty information, leading to chaos and potentially damaging consequences. Local backend, default. The starter pack. By default, when you start a new Terraform project, its state is stored in a file named Terraform TF state right in your working directory. This is called the local backend. Pros. It's simple, requires no extra setup, and is great for quick, single-user experiments or learning. Cons. No collaboration. If multiple people are working on the same infrastructure, they will each have their own local copy of the state. This inevitably leads to state drift and conflicts. Person A applies changes, Person B's local state is now outdated, and their next apply might revert person A's changes or cause unexpected behavior. No state locking. There's no mechanism to prevent multiple users from attempting to modify the state simultaneously, which can corrupt the state file. Risk of loss. If your local machine crashes or the Terraform TF state file is accidentally deleted, you lose Terraform's entire knowledge of your deployed infrastructure, forcing you into a difficult recovery process. No auditing history. The local state file typically doesn't offer versioning or an audit trail of changes. For any professional or team-based infrastructure management, the local backend is simply not sufficient. Remote backends. The cornerstone of team collaboration. To address the limitations of the local backend, Terraform supports remote backends. A remote backend stores the state file in a shared, accessible, and durable storage service, typically in the cloud. This is a fundamental step towards adopting Terraform effectively in a team environment. Benefits of remote backends. Collaboration. Multiple team members can share a single, authoritative state file, ensuring everyone is working with the most up-to-date information about the infrastructure. Durability and backup. The state is stored in a resilient, often highly available and geographically replicated, service. This significantly reduces the risk of accidental loss and provides built-in backup and versioning capabilities. State locking, crucial. Many remote backends, like AWS S3 with DynamoDB or Azure Blob Storage, provide state locking. This mechanism prevents multiple concurrent Terraform apply operations from corrupting the state file, ensuring only one operation can modify the state at a time. Security. Remote backends often allow for more robust access controls and encryption of the state file at rest and in transit. History and auditing. Services like S3 provide versioning, allowing you to revert to previous versions of your state file if needed, and offering an audit trail of changes. Common remote backend examples. AWS S3 with DynamoDB for locking. This is perhaps the most common and robust remote backend setup for Oz users. The state file is stored as an object in an S3 bucket, which provides high durability and versioning. A separate Oz DynamoDB table is used to facilitate state locking, ensuring atomicity of operations. This setup is highly recommended for AWS-centric teams. Azure Blob Storage. Similar to S3, Azure's Blob Storage provides a reliable way to store the state file, often coupled with Azure's own locking mechanisms. HashiCorp Cloud Enterprise. HashiCorp, the creators of Terraform, offer their own official solutions: Terraform Cloud SaaS and Terraform Enterprise on-prem. These are purpose-built platforms for managing Terraform, offering native remote state storage, advanced collaboration features, policy enforcement, and remote execution. For serious team usage, these managed solutions can greatly simplify Terraform adoption and operation. Other backends. Terraform also supports backends like HashiCorp Console for distributed locking and key-value storage, Google Cloud Storage, Git, though less recommended for locking, and more. Configuring a remote backend. You configure a remote backend by adding a backend block within the top-level Terraform block of your configuration. For example, setting up an AWS S3 backend, conceptually, you'd have a backend S3 block, inside which you'd specify a bucket name, e.g., my Terraform state bucket unique, and a key, e.g., prod/webserver/Terraform TF state, to define the path to the state file within the S3 bucket. You would also specify the region, e.g., us East 1, and dynamodtable, e.g., my Terraform locks. These parameters tell Terraform exactly where to store and manage its state remotely. Once this backend configuration is added to your main TF file, or a similar TF file in your root module, the very next time you run Terraform init, Terraform will detect the change. It will prompt you to migrate any existing local state file to the newly configured remote backend. After this, all subsequent operations, plan, apply, destroy, will interact directly with the remote state. State locking. Preventing concurrent modification. Imagine two engineers, Alice and Bob, simultaneously modifying the same infrastructure without coordination. Alice starts an apply operation, and while her changes are in progress, Bob starts another apply on the same infrastructure. This is a recipe for disaster. The state file could become corrupted, lead to race conditions, or cause some of one person's changes to be overwritten by the others, resulting in an inconsistent and unstable environment. State locking is the solution to this problem. When a remote backend supports state locking, it ensures that only one Terraform operation can acquire a lock on the state file at any given time. How it works, conceptually. When you run Terraform plan, if it might lead to a change or Terraform apply, Terraform first attempts to acquire a lock on the remote state via the backend. If it successfully acquires the lock, it proceeds with the operation. If another operation is already holding the lock, your operation will either wait until the lock is released or fail immediately, preventing simultaneous writes. Once your operation completes, successfully or with an error, Terraform releases the lock, making the state available for the next operation. Importance: state locking is absolutely critical for team environments and CI/CD pipelines. It prevents state corruption and ensures that infrastructure changes are applied in an orderly and predictable fashion. Always ensure your chosen remote backend supports state locking and that it's correctly configured. Sensitive data in state. The Terraform state file contains a complete snapshot of all the resource attributes that Terraform manages, including values that might be considered sensitive, such as database passwords, API keys, or private SSH keys. This presents a security concern. If your state file were to fall into the wrong hands, these sensitive credentials could be exposed. The dilemma: Terraform needs to store these values to ensure idempotence and manage the resource's lifecycle. It can't simply forget them. Best practices for handling sensitive data in state: never commit local state to version control. Your Terraform TF state file should always be included in your gitignore or equivalent for other version control systems. Directly committing local state is a major security risk and defeats the purpose of remote state. Use robust remote backends with encryption. Choose remote backends that offer strong access controls and encryption at rest. Services like Oz S3 and Azure Blob Storage provide server-side encryption for objects, which should always be enabled for your state buckets. Minimize sensitive data in outputs. If you're outputting sensitive information using output blocks, ensure you mark them with sensitive equals true. This will prevent their values from being displayed in the terminal during Terraform apply or Terraform output. Integration with dedicated secrets managers. For truly sensitive information, like production database credentials, the best practice is to separate it entirely from your Terraform state. Instead, use dedicated secrets management services like HashiCorp Vault, AWS Secrets Manager, or Azure Key Vault. Terraform can integrate with these services through data sources to retrieve secrets at runtime when provisioning resources, rather than storing them directly in the state file. This significantly reduces the attack surface. Terraform state commands, brief overview. While the golden rule is, don't manually edit the state file, Terraform provides a powerful set of Terraform state subcommands for managing the state safely and programmatically. These commands should be used with extreme caution and a clear understanding of their impact, as they directly manipulate Terraform's understanding of your infrastructure. Terraform state list lists all resources currently managed by the state file. Terraform state show resource address displays the attributes of a specific resource within the state file. Terraform state MV old address new address moves a resource's address within the state file. This is crucial when you refactor your Terraform code and change resource names or locations, allowing Terraform to recognize the resource has moved, not been deleted and recreated. Terraform import resource address cloud resourced brings an existing infrastructure resource that was created manually or by other means under Terraform's management. This is useful for adopting legacy infrastructure into an ISC paradigm. Terraform refresh updates the state file with the latest attributes from the real infrastructure. This is often done implicitly during Terraform plan and apply, but can be run explicitly to check for drift, manual changes made outside of Terraform. Terraform apply refresh only performs only the refresh operation, updating the state, but not applying any configuration changes to the real infrastructure. Useful for updating state after manual changes. Terraform taint resource address, mostly deprecated by replace, marks a resource in the state as tainted, forcing Terraform to recreate it on the next apply. It's generally better to use the replace flag with Terraform apply for clearer intent. These commands are powerful tools for state management and recovery, but should be used thoughtfully. Recap and further reading. The Terraform state file is not merely a technical detail. It's the bedrock upon which all of Terraform's operations are built. Moving from a local state to a remote backend is a critical evolution for any team looking to leverage Terraform effectively, unlocking collaboration, durability, and essential state locking. While the state contains sensitive data, adopting best practices such as encryption, strict access control, and integration with dedicated secrets managers can mitigate risks. By understanding and respecting the state's role, you gain a powerful ability to manage your cloud infrastructure safely and reliably. For comprehensive documentation on Terraform backends and their configuration options, visit the official Terraform documentation on backends for detailed security considerations regarding state files and sensitive data. Explore resources on secrets management with Terraform and Terraform state security. For more on Terraform state commands and their usage, refer to the Terraform CLI documentation subsection on state commands. Chapter 6, Organizing for Scale, Reusability with Modules and Workspaces. Introduction, from single deployments to scalable architectures. So far, we've focused on deploying single, self-contained pieces of infrastructure. You've learned how to define resources, use variables for flexibility, and understand the critical role of the state file. However, as your infrastructure grows, simply adding more resource blocks to a single file or even a single directory will quickly become unwieldy. Imagine having to copy and paste the same dozen OS instance, OS security group, and OS network interface blocks every time you need a new web server. Changes to any of these would require updating every duplicated block, leading to inconsistencies and errors. This is where organization and reusability become paramount. Just as software development relies on functions, libraries, and classes to manage complexity, infrastructure as code needs similar constructs. Terraform provides two powerful features for this: modules for encapsulating reusable infrastructure patterns, and workspaces for managing multiple, distinct environments from a single configuration. Mastering these will enable you to build scalable, maintainable, and consistent infrastructure architectures. Terraform modules, encapsulating infrastructure patterns. Think of a Terraform module as the equivalent of a function or a subroutine in a programming language. It's a self-contained, reusable packaged set of Terraform configurations that deploys a specific piece of infrastructure. A module can logically group related resources that commonly go together, like a web server with its associated security group and load balancer, or an entire virtual private cloud, VPC network setup. What are modules? A module is a declarative representation of one or more related resources or an entire infrastructure pattern. Every Terraform configuration, even a simple main.tf file in a directory, is itself a root module. When you call another set of configurations from within your root module, those are considered child modules. Why use modules? Don't repeat yourself, dry. Avoid duplicating configurations. Define an infrastructure pattern once in a module, and then reuse it many times throughout your project or even across different projects. Abstraction and encapsulation. Modules allow you to hide the complexity of underlying resources. Users of a module don't need to know the intricate details of how a VPC is set up. They just need to provide necessary inputs, like CIDR blocks, and the module handles the rest. This simplifies configuration for consumers. Consistency. By reusing the same module for similar infrastructure components, you ensure that all instances are configured consistently, reducing configuration drift and the snowflake server problem. Collaboration. Modules promote team collaboration by allowing different team members to focus on developing specific infrastructure components independently. Maintainability. Changes or updates to an infrastructure pattern only need to be made in one place, the module definition, and then those changes can be propagated to all instances that use the module. Module structure. A module is simply a directory containing Terraform configuration files, TF. A typical module directory might contain main TF, the primary configuration defining the module's resources, variables, TF, declarations for the input variables, parameters that the module accepts, outputs, DF, definitions for the output values that the module exposes to its parent, versions, TF, specifies required Terraform and provider versions, README-MD, very important for documenting the module's purpose, inputs, outputs, and usage. Creating your own module, conceptual example. Let's imagine creating a module to provision a simple web server, including an EC2 instance and its associated security group. You would create a new directory, say modules/webserver/. Inside modules/webserver/variables TF, you define input variables like instance type, e.g., string type, default T2 micro, amiid string, and VPC security group IDs, list of strings. Inside modules/webserver/main TF, you define an security group resource that allows inbound HTTP/HTTPS traffic, ports 80 and 443, and an instance resource that uses the amiid and instance type from input variables and attaches the security group. Inside modules/webserver/outputs TF, you define outputs such as instance publicip, the public IP of the EC2 instance, and security group ID, the ID of the created security group. Consuming modules, calling a module. Once you've defined a module, you can call it from your root module or another child module using a module block. There are several ways to source a module. Local path modules. For modules defined within your own repository, like our modules/webserver example, you reference them by their local file path. In your root main TF file, or a file in another calling module, you would conceptually specify a module block named MyWebServerInstance. Inside, you'd set the source attribute to /modules/webserver, the path to the module directory. Then, you'd pass values to the module's input variables, such as instance type equals T2 medium, amiid, AMIXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXX The Terraform Registry, registry.terraform.io, is a public repository of official and community-contributed modules. These are often well-documented and widely used, perfect for common infrastructure patterns like a full VPC, EKS cluster, or RDS database. Calling a registry module involves specifying a source string like HashiCorp/VPC/Oz for an Oz VPC module. You normally include a version constraint, e.g., version 3.1.0. Git modules. You can source modules directly from Git repositories, GitHub, GitLab, Bitbucket, or even private Git servers. This is common for internal, organization-specific modules not published to the public registry. The source string points to the Git repository URL, optionally with a specific branch, tag, or commit hash. For example, Git https://example.com/org/repogit?ref equals v1.2.0. Terraform will clone the repository and use the module within it. When you call a module, its outputs become available to the calling module. For example, if MyWebServer instance in our WebServer module example produced an instance.epiblissip output, you could reference it as module.mywebserverinstance.instance.epiblissip. Terraform workspaces, managing multiple environments, while modules help with horizontal reuse, packaging components for repeated deployment, workspaces help with vertical scaling, managing different logical environments of the same configuration. Workspaces allow you to provision multiple distinct instances of your infrastructure that are managed by the same Terraform configuration. What are workspaces? When you first initialize a Terraform project, it starts with a default workspace named default. Every time you run Terraform apply, it operates within the context of the currently selected workspace. Each workspace maintains its own isolated state file. This isolation allows you to deploy exactly the same Terraform configuration multiple times without interfering with each other. Why use workspaces? The primary use case for workspaces is to manage separate, non-overlapping environments for the same infrastructure configuration. Common examples include development, staging, production. You can use the same Terraform files to deploy identical infrastructure for your dev, staging, and prod environments, each with its own state and resources. Feature branches personal sandboxes. Developers might create temporary workspaces for their isolated testing environments. Workspaces versus separate directories, the great debate. This is a design decision many teams grapple with. Using workspaces. Pros: keeps all environment configurations, using variables, which can change per workspace within a single root directory. Simplifies switching between environments. Good for nearly identical infrastructure, where only variable values change per environment, e.g., instance count, sizing, region. Cons: can become complex if environments diverge significantly, e.g., production has special resources not present in dev. Commands, like Terraform plan, need to be accompanied by Terraform workspace select or TF workspace environment variable, which can be forgotten. Not all backends fully support workspace-specific paths. Using separate directories. Pros: clear separation of concerns. Each environment, e.g., environment/dev, environments prod is its own root module, allowing for significant divergence in configurations if needed. Simpler mental model for some. More explicit. Cons: more boilerplate if environments are largely identical, copying configuration files. Changes to common parts of the infrastructure need to be synchronized across multiple directories. General recommendation. For most scenarios, especially when different environments have slightly different resource types or significant configuration differences, separate directories for each environment, each acting as its own root module, is often cleaner and easier to manage than relying heavily on workspaces. Workspaces are best suited for creating truly isolated and mostly identical copies of an environment, e.g., creating multiple dev sandboxes or spinning up multiple temporary test environments. Terraform workspace commands. Terraform workspace list lists all available workspaces and indicates the current one. Terraform workspace show displays the name of the current workspace. Terraform workspace new name creates a new workspace and switches to it. This also creates a new state file for that workspace. Terraform workspace select name switches to an existing workspace. All subsequent Terraform plan and Terraform apply commands will operate on the state file associated with this workspace. Terraform workspace delete name deletes an empty workspace. You cannot delete the currently selected workspace or a workspace that still contains resources. You would destroy resources first, then switch away, then delete. When you switch workspaces, you'll notice in your S3 backend that the state file path will often include the workspace name, e.g., prod/webserver/dev/terraform/tf state becomes prod/webserver/staging/terraform/tf state. This is how the backend keeps the states isolated. Recap and further reading. Modules and workspaces are essential tools for managing complexity and promoting consistent, scalable infrastructure deployments with Terraform. Modules allow you to package and reuse common infrastructure patterns, promoting the dry principle and abstracting away complexity. Workspaces provide a mechanism to manage multiple, isolated deployments of the same Terraform configuration, primarily for different environments. While separate directories often offer stronger isolation for distinct environments, workspaces are powerful for creating functionally identical copies of environments. By effectively leveraging both, you can structure your Terraform code to be maintainable, adaptable, and collaborative, enabling you to manage infrastructure at scale. For in-depth understanding of module best practices and structure, refer to the Terraform documentation on modules and HashiCorp's official module usage guides. For more detailed comparisons and examples on workspace usage, search for community articles or HashiCorp Learn guides comparing Terraform workspaces versus folders. To explore pre-built and robust modules, browse the public Terraform registry. Chapter 7. Advanced Terraform Techniques, Conditionals, Loops, and Functions. Introduction. crafting intelligent infrastructure. In our journey so far, we've covered the foundational elements of Terraform. We've learned to define basic resources, parameterize our configurations with variables, organize larger projects into reusable modules, and manage different environments with workspaces. These tools are powerful, but sometimes you need to go beyond simply defining static resources. What if you need to create a specific number of similar virtual machines, or configure a resource differently based on unique identifiers, or even dynamically generate portions of a configuration based on a list of inputs? Terraform, powered by its HashiCorp configuration language, HCL, offers several advanced techniques to bring more dynamism, expressiveness, and intelligence to your infrastructure code. This chapter explores metarguments like count and foretch for creating multiple resources, dives into Terraform's rich library of built-in functions for data manipulation, introduces conditional expressions for if-then-else logic, and explains dynamic blocks for generating repetitive nested configurations. Mastering these techniques will elevate your Terraform skills, allowing you to write more concise, flexible, and powerful infrastructure blueprints. Meta-arguments, beyond basic resource definition, beyond the typical arguments used to configure a resource, like an instance type for a server, Terraform provides special meta-arguments that apply to all resource and module blocks. These arguments control how Terraform processes and manages the blocks themselves, rather than defining attributes of the cloud resource. The most common and powerful are count and foretch. The count meta-argument, deploying multiple identical resources. Imagine you need to deploy 5 identical web servers. Instead of writing 5 separate resource, ausinstance, blocks, each with the same configuration, you can use the count meta-argument. Purpose allows you to create multiple instances of a resource or module based on a simple numerical count. How it works. When you add a count argument to a resource block and set its value to an integer, Terraform will create that exact number of resources. Inside the resource block, you can then access a special count.index variable, which provides the current zero-based iteration number, 0, 1, 2, etc. This count.index is crucial for differentiating between the instances, such as by appending it to a resource name. Example: to create 3 identical EC2 instances for an application layer, you would declare an ausinstance resource and set its count attribute to 3. Inside that resource's settings, when creating a name for the server, you could use count.index to generate names like WebServer 0, WebServer 1, and WebServer 2. This ensures each server has a unique identifier while sharing the same base configuration template. Conditional creation. Count is also frequently used for conditional resource creation. By setting count to either 1 to create the resource, or 0 to not create the resource, based on a Boolean variable, you can effectively enable or disable entire blocks of infrastructure. For example, if you have a variable feature-enabled set to true, you create an associated resource, count1. If false, you don't, count 0. The foretch meta-argument. Dynamic properties from collections. While count is excellent for identical resources based on a number, sometimes you need to create resources where each instance has a unique, distinct property, or where the number of instances is determined by the size of a map or a set. This is where foretch shines. Purpose allows you to create multiple instances of a resource or module for each element in a given map or set of strings. This is powerful for handling resources with distinct names or properties derived from a collection. How it works: you assign foretch to a map or a set. Terraform then creates one instance of the resource for each element in the collection. Inside the resource block, you can access each key and each value, if using a map, to configure the specific attributes of that instance. Example: imagine you need to create multiple security groups, each allowing traffic from a specific port range for different applications, e.g., one for web, one for database, one for a custom service. You could define a map variable where the keys are the application names, web, database, and the values are the associated port numbers. Then, using foretch on this map inside an auSecurity group resource, you can dynamically create a separate security group for each application, using each key for the group name and each value for the ingress port. This results in groups like WebSG allowing port 80 and DatabaseSG allowing port 3306, all from a single resource definition. 4H vs count. Use count when you need a specific number of identical resources, and you don't have a natural unique identifier for each instance other than its numerical index. Use 4H when you have a collection of distinct items, like a list of desired security group names or a map of user credentials, and you want to create one resource for each item, allowing unique properties for each. 4H also generally results in more stable state management when individual items are added or removed from the collection. The lifecycle meta-argument. Customizing resource behavior. The lifecycle block is a special meta-argument that allows you to customize Terraform's default behavior when managing resources. It's used for advanced scenarios and to add safeguards. Purpose: to define specific rules about how a resource should be treated during Terraform operations beyond its normal create, read, update, delete cycle. Key settings. Prevent destroy equals true. This is a crucial safety mechanism, especially for production environments. If set to true on a resource, Terraform will prevent any user from accidentally destroying that resource, e.g., by running Terraform destroy or by removing it from the configuration. Terraform will throw an error instead, requiring manual intervention to temporarily disable this flag before destruction is allowed. Highly recommended for critical assets like production databases or core networking components. Create a buffer destroy equals true. Sometimes, when an attribute of a resource changes, the cloud provider requires Terraform to destroy the old resource and create a new one in its place. This can lead to downtime. If create a buffer destroy is set to true, Terraform will first create the new resource with the updated configuration, then update any dependencies to point to the new resource, and only then destroy the old one. This is excellent for achieving zero downtime updates for resources that support it. Ignore changes allows you to tell Terraform to ignore changes to specific attributes of a resource after it's been created. This is useful when certain attributes are modified by an external process or by manual intervention, and you don't want Terraform to continually drift and try to revert those changes. For example, if a monitoring agent updates a server's tag, you might tell Terraform to ignore changes to that specific tag. Built-in functions. Manipulating data in HCL. Terraform's configuration language, HCL, is not a full-fledged programming language, but it includes a rich set of built-in functions designed to perform common transformations and manipulations on data types within your configuration. These functions allow you to process strings, work with lists and maps, perform mathematical operations, and encode-decode data, making your configurations more dynamic and concise. Purpose: to transform, combine, or extract information from variables, resource attributes, or other data sources, allowing for more complex computations and flexible configurations. How to use. Functions are called using the syntax function name, argument 1, argument 2. The output of a function can then be used as the value for a resource argument, a variable default, or an output. Common categories with conceptual examples. String functions. Join combines a list of arguments into a single string with a separator. Imagine joining elements from a list of machine roles, web, app, db, with a hyphen to create a server name like webappdb. Split divides a string into a list based on a delimiter, useful for parsing a single input string containing multiple values into a list. Upper/lower converts string to uppercase lowercase, for consistent naming conventions. Subster extracts a portion of a string. Collection functions, lists, and maps. Length returns the number of elements in a list or map, useful with count for dynamic scaling. Concat joins multiple lists together. Lookup retrieves a value from a map by key, with a default fallback if the key isn't found. Keys/values extracts all keys or values from a map into a list. Contains checks if a list contains a specific value. SetProduct calculates the Cartesian product of multiple lists, useful for creating combinations. Numeric functions. Min, max, ceil, floor, standard mathematical operations. Encoding decoding functions. Base64 encode, base64 decode, JSON encode, JSON decode for handling data formats often required by cloud APIs. File system functions. Filebase64, template file for reading content from local files, useful for user data scripts for servers or IAM policies. By combining these functions, you can express complex logic directly in your HCL, avoiding the need for external scripting. Conditional expressions. Terraform allows you to implement simple, if-then-else, logic directly within your configuration using conditional expressions. This enables you to dynamically set the value of an attribute or variable based on a specific condition. Purpose: to make decisions within your configuration, allowing attributes to vary based on environmental factors, variable inputs, or other conditions. Syntax: the general form is condition, true value, false value, condition, an expression that evaluates to a Boolean true or false. True value, the value to use if the condition is true. False value, the value to use if the condition is false. Practical use cases: environment-specific settings, setting a resource's instance type based on an environment variable. For example, var environment == production. T3 large, T3 micro. This would use a larger instance in production and a smaller one elsewhere. Optional attributes, providing a value for an attribute only if a certain variable is set, otherwise using a default or null. Dynamic naming, adjusting parts of a generated name based on a flag. Conditional expressions are a concise way to inject logic directly into your resource definitions, making them more adaptable without resorting to count or for-each if only one resource is being created. Dynamic blocks, generating nested configuration. Some Terraform resource types require nested configuration blocks, like ingress-egress rules for security groups, tags, or certain policy statements in IAM. When the number or content of these nested blocks needs to be dynamic, meaning they depend on a list or map of input values, you use dynamic blocks. Purpose: to generate repetitive nested blocks within a resource or data source configuration based on a list or map of values, similar to how for-each creates multiple resources. Why needed? Imagine a security group that needs to allow traffic from a variable list of IP addresses. Instead of manually writing an ingress block for each IP, a dynamic block can iterate over a list of IPs and generate an ingress rule for each one. This keeps your configuration clean and flexible. How it works: you use the dynamic keyword followed by the name of the nested block type, e.g., dynamic ingress. Inside the dynamic block, you use a for-each expression to iterate over a collection list or map. Within the content block, you define the attributes for each generated nested block, accessing each key and each value from the iteration. Example: for an AWS security group, you might have a variable that is a list of port numbers you want to open. A dynamic ingress block could then iterate over this list. For each value, a port number. It would create an ingress block setting from port and top port to that each value, and the protocol to TCP, while allowing access from any IP address, 0.0.0.0/0. This allows you to control a security group's allowed ports simply by modifying a variable that is a list of numbers, rather than adding or removing individual ingress definition blocks. Recap and further reading. By mastering count and for-each for creating multiple resources, leveraging Terraform's extensive built-in functions for data manipulation, applying conditional expressions for dynamic attribute assignment, and using dynamic blocks for flexible nested configurations, you unlock a new level of power and flexibility in your infrastructure as code. These techniques enable you to write more abstract, adaptable, and concise Terraform configurations, capable of handling complex scenarios and a wider range of infrastructure patterns with elegance and control. You are no longer just writing static instructions. You are building intelligent, self-adapting infrastructure blueprints. For comprehensive lists and detailed explanations of all available built-in functions, refer to the Functions section in the official Terraform language documentation. For in-depth examples and best practices on using count and for-each effectively, search for specific HashiCorp Learn tutorials or documentation pages on these meta-arguments. For more details on lifecycle rules, Look for the dedicated lifecycle documentation within Terraform's official HCL reference. For examples on complex dynamic block scenarios, explore the Dynamic Blocks section in the Terraform language documentation. Chapter 8, Securing Your Infrastructure, Best Practices with Terraform. Introduction, Security by Design. As we progress through building and managing infrastructure with Terraform, it's crucial to shift our mindset from merely provisioning resources to provisioning secure resources. In the cloud, security is not an afterthought or a separate department's responsibility. It's an integral part of every infrastructure decision. Treating infrastructure as code presents a unique opportunity to embed security directly into your blueprints, ensuring consistency, auditability, and immediate adherence to best practices. This concept, often called security by design or shift-left security, means identifying and mitigating security risks as early as possible in the development lifecycle. This chapter will delve into key security considerations when using Terraform, focusing on how to implement the principle of least privilege, handle sensitive data with care, enforce network security, prevent accidental destruction of critical assets, and integrate with auditing and policy as code concepts. Building secure infrastructure with Terraform isn't just about avoiding breaches. It's about building trust, ensuring compliance, and fostering a resilient cloud environment. Principle of least privilege with IAM. The principle of least privilege, POLP, is a fundamental security concept. Systems and users should only be granted the minimum permissions necessary to perform their intended function, and no more. Applying POLP diligently significantly reduces the attack surface and limits the potential damage from a compromised account or system. Terraform's role in IAM definition. Terraform itself doesn't grant permissions to itself to deploy resources. That's handled by your Oz credentials for CLI or IAM roles for CI/CD. Rather, Terraform is a powerful tool for defining and provisioning IAM, identity and access management, resources within AWS, or similar services like Azure AD for Azure, or GCP IAM for Google Cloud. This includes IAM users, creating programmatic users with specific access keys for applications. IAM roles, defining roles that can be assumed by EC2 instances, Lambda functions, or other AWS services to grant them temporary, limited permissions. This is the preferred method for granting permissions to Oz services and applications, over using access keys directly on instances. IAM policies, crafting granular JSON policies that specify what actions, e.g. S3, getObject, EC2, run instances are allowed or denied on which resources, e.g. ARN, Oz, S3, mybucket/. Best practices for IAM with Terraform. Granular policies. Instead of broad permissions, e.g. S3, for all S3 actions, define policies that specify only the exact actions and resources needed. If an application only needs to read from a specific S3 bucket, its policy should reflect that. Managed policies versus inline policies. Prefer AWS managed policies for common use cases, e.g., S3 read-only access, as they are maintained by Oz. For custom, application-specific permissions, use customer-managed policies in Terraform, which are independent resources that can be attached to multiple users' roles groups. Avoid inline policies, policies directly embedded in a user role group definition for reusability and auditability. Roles, not users, for applications. Configure IAM roles for your cloud resources, e.g., an EC2 instance running a web application. The instance assumes this role, granting it temporary credentials, which are automatically rotated by Oz. This is far more secure than distributing static access keys to instances. Review and audit. Regularly review your IAM policies and roles defined in Terraform. The codified nature makes this easier than manual review, as you can use Git commit history to track changes. Handling sensitive data. Secrets management. The Terraform state file can, by its nature, store sensitive data, like database passwords, API keys, private keys if generated by Terraform, in plain text or easily reversible formats. This is a significant security risk. exposure of your state file could lead to compromise of your entire infrastructure. The problem? Terraform needs these values to configure resources. For example, if Terraform creates an RDS database, it knows the password it set. Best practices for sensitive data: never store secrets in Git. Your TF configuration files that you commit to Git should never contain hard-coded sensitive data. This includes passwords, API keys, private certificates, or any credential. Use sensitive equals true for variables and outputs. For variable declarations, variable DB password, sensitive equals true. This prevents the value from being displayed in Terraform plan or apply outputs. For output declarations, output adminipike, value equals osipigate value sensitive equals true. This redacts the value when Terraform output is run. Secure remote state. Ensure your chosen remote state backend, e.g., AWS S3, is configured with strong access controls, least privilege IAM policies for the bucket, and server-side encryption, SSE. S3 versioning helps against accidental overwrites. Integrate with dedicated secrets managers. This is the gold standard. For genuinely sensitive, long-lived credentials, do not let Terraform store them directly in the state. Instead, use a dedicated secrets management service, AWS Secrets Manager. For AWS environments, it provides secure storage, automatic rotation, and fine-grained access control for sensitive data. HashiCorp Vault, a widely used, open-source tool for centralized secrets management, ideal for multi-cloud or hybrid environments. Azure Key Vault/Google Secret Manager, equivalent services for Azure and GCP, respectively. How it works conceptually. Terraform interacts with these services using data sources, e.g., data, secret version, DB credentials. These data sources fetch the secret at runtime during a Terraform apply, feed it into the resource configuration, e.g., for a database password, and the secret is never written to the state. This ensures that the state file only contains a reference to the secret, not the secret itself. Security groups and network access control lists, ACLS. Network security is fundamental. Terraform allows you to define every aspect of your cloud network security, including security groups, SGS. Stateful virtual firewalls that control inbound and outbound traffic for individual resources, like EC2 instances, RDS databases, load balancers. Network ACLS, NACLs. Stateless firewalls that operate at the subnet level, providing a second layer of defense. Best practices for network security with Terraform. Least privilege for network access. Configure security groups to allow only the minimum necessary inbound and outbound traffic. For example, a web server might only need inbound port 80, HTTP, and 443 HTTPS from the internet, and outbound port 443 to a database. Use specific CIDR blocks. Instead of 0.0.0.0/0, allow from anywhere. For ingress rules, specify the narrowest possible IP ranges, CIDR blocks, that need access. For internal communication, reference other security group IDS directly, e.g., allow traffic from SG 12345 instead of specific IPS. Separate and segment. Define distinct security groups for different tiers of your application, e.g., Web Tier SG, App Tier SG, DB Tier SG. This allows for strict segmentation. Centralized network configuration. If possible, define core network components, VPCs, subnets, NACLs, in a separate Terraform module or configuration from your application deployments. This provides a clear boundary and simplifies management. Review rules regularly. Network rules can become complex. Leverage Terraform's code nature to easily review and audit your network security rules. Encryption at rest and in transit. Protecting data is paramount, whether it's stored at rest or moving across a network in transit. Terraform can enforce encryption for many resource types. Encryption at rest, ensuring data is encrypted when stored on disk. Storage services, configure S3 buckets with default encryption, e.g., AWS S3 OS bucket resource with server-side encryption configuration block. Databases, enable encryption for database instances, e.g., OSP instance with storage encrypted equals true. Block storage. Ensure EBS volumes are encrypted. OSP volume or OS instance automatically encrypts its root volume if set up. Snapshots. Encrypt database snapshots and AMI backups. Key management. Use cloud provider key management services, KMS, like AWS KMS, Azure Key Vault, or GCP KMS to manage encryption keys. Terraform can specify which KMS key to use. Encryption in transit. Ensuring data is encrypted as it moves between components. Load balancers. Configure application load balancers, ALBS, or network load balancers, NLBS, with HTTPS listeners, managing SSL TLS certificates, e.g., OSLB listener with SSL policy and certificatorn. Use AWS Certificate Manager, ACM, to provision and manage certificates. Direct Connect. Provision secure connectivity back to on-premises networks using VPNs or Direct Connect, configured via Terraform. Preventing accidental destruction. Safeguards and permissions. Given the power of Terraform to create and destroy entire environments, safeguards against accidental deletion are critical, especially for production or persistent resources. Prevent Destroy Lifecycle Rule. As covered in Chapter 7, the lifecycle blocks prevent destroy equals true setting is your primary line of defense within the Terraform configuration. It will throw an error if you attempt to destroy the resource. This is ideal for production databases, main VPCs, logging buckets, etc. IAM permissions. Complementing prevent destroy, rely on Oz or other cloud IAM policies. Create specific IAM roles for deployments and ensure they do not have EC2, terminate instances, S3. Delete bucket or other destructive permissions on production resources unless absolutely necessary and coupled with strict approval processes. Terraform Plan Review. The Terraform Plan output acts as a final human gate. Always review the plan carefully, especially if it shows resources being destroyed or modified in unexpected ways. Multi-factor authentication, MFA. Enforce MFA for all AWS accounts, especially root and administrative users. Terraform Plan Destroy. If a Terraform destroy operation is intended, run Terraform Plan Destroy first to explicitly visualize all resources that will be removed. Auditing and compliance. Infrastructure as code, by its very nature, brings unprecedented levels of auditability. Your entire infrastructure definition is version-controlled in Git, meaning every change, who made it, and when, is logged. Source of truth. Your Terraform code becomes the definitive blueprint of your infrastructure. This simplifies compliance audits, as auditors can review the code rather than trying to piece together manual configurations. Integration with cloud auditing. Services like AWS CloudTrail, Azure Monitor, and GCP Cloud Logging record all API calls made to your cloud resources. Since Terraform communicates via API calls, these logs capture every action Terraform performs, providing a full audit trail of resource creation, modification, and deletion. Policy as code, conceptual. Beyond simply defining infrastructure, tools are emerging that allow you to define and enforce organizational policies before infrastructure is deployed. HashiCorp Sentinel, for Terraform Enterprise, and Open Policy Agent OPA are examples. They allow you to write policies, e.g., all S3 buckets must be encrypted. No EC2 instance can be deployed without specific tags that are checked during the Terraform plan stage, preventing non-compliant deployments from ever reaching your cloud environment. Recap and further reading. Security is not a checkbox. It's an ongoing process and a shared responsibility. Using Terraform allows you to embed security principles directly into your infrastructure blueprints, moving from a reactive to a proactive security posture. By diligently applying the principle of least privilege, carefully handling sensitive data via dedicated secrets managers, hardening your network through security groups and NACLs, enforcing encryption, protecting against accidental destruction, and leveraging the auditability of ISC, you can significantly enhance the security posture of your cloud environments. Embracing these best practices from the start will lay a strong foundation for resilient, compliant, and trustworthy infrastructure. For in-depth Oz security best practices, refer to the Oz Well-Architected Frameworks security pillar. Similar frameworks exist for Azure and GCP. For detailed information on configuring backend security, S3 bucket policies, encryption, consult cloud provider documentation for your chosen backend. For more on secrets management, best practices with Terraform, search for resources on Terraform and Secrets Managers or HashiCorp Vault integration with Terraform. To explore policy as code tools, research HashiCorp Sentinel and Open Policy Agent OPA. Chapter 9, Automating the Pipeline, Terraform in CI/CD environments. Introduction, Bridging Development and Operations. In today's fast-paced digital world, the ability to deliver software rapidly and reliably is paramount. Infrastructure as code, as you've seen, is a cornerstone of this agility, allowing you to define your cloud resources in version-controlled blueprints. But simply having code doesn't guarantee speed or consistency. You need to integrate it into an automated delivery process. This is where continuous integration, CI, and continuous delivery deployment, CD pipelines come into play. Treating your infrastructure configurations with the same rigor as application code and integrating them into CI/CD pipelines is a hallmark of mature DevOps practices. It means that every change to your Terraform code, whether it's adding a new server, updating a security group, or deploying an entirely new application, goes through automated tests, a consistent build process, and a controlled deployment mechanism. This chapter will explore why CI/CD is crucial for Terraform, outline the core principles for integrating it, provide a conceptual overview of common CI/CD tools, and introduce dedicated platforms like Terraform Cloud that streamline this process. Why CI/CD for infrastructure? Integrating Terraform into a CI/CD pipeline brings significant benefits that amplify the advantages of infrastructure as code. Faster deployments. Automated pipelines eliminate manual steps, reducing the time from code commit to infrastructure provisioning from hours or days to minutes. Reduced errors and increased consistency. Manual deployments are prone to human error. Automation ensures that the same steps are executed every time, eliminating configuration drift and snowflake environments between development, staging, and production. Continuous feedback. Automated tests within the pipeline can quickly identify issues in your Terraform code, syntax errors, security policy violations, potential cost implications before they reach production. Version control as source of truth. Every infrastructure change is triggered by a commit to version control, e.g., Git, providing a clear audit trail and rollback capability. Increased collaboration and trust. Developers and operations teams share a common, automated process, fostering better collaboration and confidence in infrastructure changes. Secure operations. Credentials used by the pipeline can be rotated and managed securely, reducing the risk of exposure. Core principles for Terraform in CI/CD. To successfully integrate Terraform into your CI/CD pipeline, consider these fundamental principles. Version control everything. Your entire Terraform configuration, all TF files, modules, etc., must reside in a version control system. Git is the industry standard. This enables tracking changes, collaboration through pull requests, and the ability to revert to previous working states. Automated Terraform plan on pull request, PR, the golden rule. Any change to infrastructure code should initiate an automated Terraform plan in the CI pipeline as soon as a pull request is opened. Purpose. This provides immediate feedback on the impact of the proposed changes. The plan output, what resources will be added, changed, or destroyed, can then be commented directly onto the pull request, allowing team members to review the precise infrastructure implications before merging. This is invaluable, as it reveals potential issues or unexpected changes early. Human review. While automated, the plan output serves as a crucial point for human review and approval before merging to the main branch. Automated Terraform apply on merge. Once a pull request is reviewed and merged into the main or designated deployment branch, e.g., main, master, production, the CI/CD pipeline should automatically trigger a Terraform apply. Non-interactive mode. In a CI/CD pipeline, there's no human to type yes. Terraform's apply command can be run in a non-interactive mode using the auto-approve flag. This flag should only be used in trusted, automated environments where the plan has been thoroughly reviewed and approved. Environment-specific triggers. You might configure separate pipelines or stages for different environments, e.g., merge to dev branch deploys to development, merge to main deploys to staging after feature branch. Manual approval for production deployments. Centralized and secure remote state. As discussed in Chapter 5, using a remote backend, like AWS S3 with DynamoDB or Terraform Cloud, is non-negotiable for team environments. In CI/CD, this becomes even more critical, ensuring that the pipeline is always working with the definitive, up-to-date state of your infrastructure. State locking. The remote backend state locking mechanism is vital here, preventing concurrent deployments from corrupting the state file. Secure credential management. The CI/CD pipeline needs credentials, API keys, secret keys, cloud roles to authenticate with your cloud provider and perform Terraform operations. Never hardcode credentials. Store them securely in secrets managers provided by your CI/CD platform, e.g., GitHub Actions secrets, GitLab CI/CD variables, Jenkins credentials store, or integrate with dedicated secrets managers like AWS Secrets Manager or HashiCorp Vault. Principle of least privilege. Configure the credentials used by the pipeline to have only the specific IAM permissions required to execute the Terraform operations for that environment. For example, a production pipeline should only have write access to production resources. IAM roles for CI/CD runners. If your CI/CD platform runs on cloud instances, e.g., GitHub Actions, self-hosted runners on EC2, configure an IAM role for the runner instance itself, allowing it to assume an IAM role with appropriate permissions for the Terraform deployment. This is generally the most secure approach, as no long-lived credentials need to be stored directly in the CI/CD system's configuration. Immutable infrastructure and configuration. Once an infrastructure component is deployed, avoid manual changes to it. Any desired modifications should be made by updating the Terraform code in version control and letting the CI/CD pipeline deploy the change. This helps maintain consistency and ensures your code remains the true source of truth. Common CI/CD tools, conceptual overview. Many CI/CD platforms can orchestrate Terraform deployments. While the specifics vary, the general flow remains similar. GitHub Actions, a built-in CI/CD service within GitHub. You define workflows using YAML files in your repository. It offers extensive community actions, including those for Terraform. GitLab CI/CD, integrated into GitLab using GitLab SciML files. It has robust support for runners, environments, and secrets management. Jenkins, an open-source automation server. Highly flexible and extensible with a vast plugin ecosystem, but requires more setup and maintenance. Circle CI, Travis CI, Azure DevOps Pipelines, AWS Code Pipeline. Other popular commercial and cloud-native CI/CD services that offer similar capabilities. Conceptual CI/CD workflow with an example. Let's trace a simplified, conceptual CI/CD workflow for deploying a web application's infrastructure changes using Terraform, without diving into specific YAML code, which won't translate to an audiobook. Scenario: a development team wants to add a new server to their application's staging environment. Developer action, local. A developer modifies a server count variable in their Terraform configuration from 1 to 2 and adds a new auth instance resource in their main.tf file. They commit these changes to a new feature branch and push it to the Git repository. Pull request, CI automated. The developer opens a pull request PR from their feature branch to the staging branch or main if main directly deploys to staging. CI pipeline trigger. The PR opening triggers a CI pipeline workflow. Stage 1, validation and formatting. The pipeline downloads the Terraform code from the PR branch. It runs Terraform validate to check for syntax errors. It runs Terraform FMT check equals true to ensure code formatting consistency. If formatting is off, it fails, prompting the developer to fix it. Stage 2. Plan generation. The pipeline runs Terraform init to download providers for the specific environment configuration using remote backend settings. It then executes Terraform plan input equals false out equals tf plan. The out flag saves the plan to a file. Context. The pipeline accesses Oz credentials securely, e.g., by assuming an IAM role with permissions for the staging environment. Output comment. The pipeline captures the detailed Terraform plan output from the tf plan file and posts it as a comment directly on the pull request. This shows plan: 1 to add, 0 to change, 0 to destroy, with details of the new server. Review and approval. Team members review the PR, scrutinize the Terraform plan output, and discuss any implications, e.g., cost, security. If satisfactory, they approve the PR. Merge and deployment, CD automated. The PR is merged into the staging branch. CD pipeline trigger. The merge event triggers another or continues the existing CI/CD pipeline run. Stage 3. Automated apply. The pipeline pulls the merged code from the staging branch. It reruns Terraform init. It then executes Terraform apply auto-approve TF plan using the plan file generated and approved earlier or generating a fresh one. Execution. Terraform interacts with Oz using the pipeline's secure credentials, provisioning the new server in the staging environment. Status update. The pipeline updates the git commit status, indicating success or failure. Post-deployment, optional. The pipeline might run automated tests against the newly deployed infrastructure, e.g., ping the new server, check if the web application is responding. It could trigger other application deployment pipelines. This structured process ensures that infrastructure changes are transparent, reviewed, and consistently applied, reducing risk and accelerating delivery. Terraform Cloud, Terraform Enterprise, dedicated platforms. While general-purpose CI/CD tools can run Terraform, HashiCorp offers dedicated platforms: Terraform Cloud, a SaaS offering, and Terraform Enterprise, an on-premises version, which are designed specifically for Terraform workflows. Key features: managed remote state and locking, provides a highly reliable and secure managed remote state backend with built-in state locking. Remote operations. Terraform Cloud can execute, plan, and apply operations on its own infrastructure. Remote runs, removing the need for local CLI installations or managing CI/CD runners specifically for Terraform. This improves consistency and security. Team and governance features. Offers fine-grained access control, team management, and organization-wide features. Policy as Code, Sentinel. Integrates HashiCorp's Policy as Code framework. Sentinel, allowing organizations to define custom policies that enforce compliance, security, and cost controls directly within the Terraform workflow, e.g., no public S3 buckets. Only approved instance types. Violations can block apply operations. Private module registry provides a centralized, private registry for sharing and reusing your organization's internal Terraform modules. Cost estimation. Some versions include features to estimate the cost of proposed infrastructure changes during the plan phase. GUI for runs and approvals. Provides a web interface to view plan outputs, manage workspaces, and approve runs, making it accessible even to non-CLI users. Terraform Cloud and Enterprise streamline the adoption of advanced Terraform practices, especially for larger organizations or those prioritizing dedicated governance and collaboration features. Recap and further reading. Integrating Terraform into your CI/CD pipeline is a powerful step towards mature DevOps practices. It accelerates infrastructure delivery, enhances reliability, reduces errors, and strengthens security by ensuring consistent, automated deployments driven by version-controlled code. By following principles of automated planning and applying, secure credential management, and leveraging specialized platforms like Terraform Cloud, your organization can achieve true infrastructure agility and maintain a robust, auditable operational posture. Treat your infrastructure as a primary part of your software delivery pipeline and unlock the full potential of infrastructure as code. For specific setup instructions on various CI/CD platforms with Terraform, Refer to the official HashiCorp Learn guides for Terraform with GitHub Actions, GitLab CI/CD/Jenkins, etc. To delve deeper into Terraform Cloud's capabilities, explore the Terraform Cloud documentation and guided tutorials on the HashiCorp website. For more on policy as code, research HashiCorp Sentinel and Open Policy Agent OPA integration with Terraform. Chapter 10. Real-world scenarios, common deployments and troubleshooting. Introduction, from theory to practice. Up to this point, we've laid a solid theoretical foundation for infrastructure as code with Terraform. We've explored its core components, learned to inject dynamism with variables and functions, organized our code with modules and workspaces, and understood the critical role of state management and security. Now, it's time to bring these concepts together and see how they apply to building common, practical infrastructure patterns. This chapter will walk through two typical cloud deployment scenarios and, just as importantly, equip you with strategies for troubleshooting common issues that inevitably arise when working with infrastructure. Learning to diagnose and resolve problems effectively is an indispensable part of your Terraform journey. Scenario 1. Deploying a simple static website on AWS S3 and CloudFront. One of the most cost-effective and scalable ways to host a static website, like a personal portfolio, a blog, or a company landing page, on AWS is by combining S3 for storage and CloudFront as a content delivery network, CDN. The use case: you have HTML, CSS, JavaScript files, and images for your website. You want them to be highly available, load quickly for users worldwide, support a custom domain like www.yourwebsite.com, and be served securely over HTTPS. The building blocks: AWS services, Amazon S3, simple storage service. This is where your website's files will physically reside. An S3 bucket can be configured to host a static website directly. Amazon CloudFront, a global content delivery network, CDN, service that caches your website content at edge locations worldwide. When a user requests your site, CloudFront serves it from the nearest edge location, dramatically reducing latency. It also provides HTTPS support for custom domains and advanced features like WAF, Web Application Firewall. Amazon Route 53, Oz highly available and scalable domain name system, DNS, web service. It translates human-readable domain names, like yourwebsite.com, into numerical IP addresses that computers use to connect to each other. Conceptual Terraform flow. Your Terraform configuration would orchestrate these services, ensuring they are provisioned and configured in the correct order, leveraging Terraform's implicit dependency management. S3 bucket. First, you would declare an OS3 bucket resource. You'd set its bucket argument to your desired website name, e.g., www.yourwebsite.com. Crucially, you would enable static website hosting on this bucket within its configuration. Permissions are vital. An OS3 bucket policy resource would be defined to allow CloudFront and potentially anonymous users, depending on your setup, to read objects from this S3 bucket. CloudFront distribution. Next, an OS CloudFront distribution resource would be defined. Its configuration would specify the S3 bucket as its origin. This is where you would also typically set up HTTPS, perhaps using a certificate managed by AWS Certificate Manager, which can also be provisioned by Terraform, and specify the custom domain names, e.g., yourwebsite.com, www.yourwebsite.com. CloudFront automatically pulls content from your S3 bucket. Route 53 DNS record. Finally, an OS Route 53 record resource would be created. This record would map your custom domain, e.g., www.yourwebsite.com, to the CloudFront distribution's unique domain name. This is often an alias record, which points to Oz resources directly. Interdependencies. Terraform seamlessly handles the order. The S3 bucket must exist before CloudFront can use it as an origin. CloudFront must be provisioned before Route 53 can point a domain to it. Terraform understands these relationships automatically. After deployment, when a user types your custom domain into their browser, Route 53 directs them to CloudFront, which efficiently serves your static files stored in S3. Scenario 2. setting up a basic web application infrastructure. Most modern web applications consist of multiple layers. A network, where communication occurs, compute resources, where the application logic runs, and perhaps load balancing to distribute incoming traffic. Terraform is perfect for defining such multi-tiered architectures. The use case: you need to deploy a simple web application that runs on a couple of virtual servers, accessible via a web browser, and includes a private database. The building blocks: AWS services, Amazon VPC, virtual private cloud, your logically isolated section of the AWS cloud. Everything else resides within this private network. Subnets, divisions within your VPC. Typically, you'd have public subnets for internet-facing resources like load balancers and private subnets for application servers and databases. Internet Gateway, IGW, allows communication between your VPC and the internet. Attached to the VPC. Route tables control network traffic routing within your VPC subnets, e.g., sending internet-bound traffic to the IGW. Security groups, stateful firewalls that control traffic to and from individual resources. Amazon EC2 instances, your virtual servers where the web application code runs. Application Load Balancer, ALB, distributes incoming web traffic across your EC2 instances, ensuring high availability and fault tolerance. Amazon RDS, Relational Database Service, a managed database service for your application's data, typically placed in private subnets. Conceptual Terraform flow. The provisioning sequence generally follows a logical network compute load balancing pattern. Network Foundation, VPC. You define an OSP resource with a specific CIDR block, your private IP range. Subnets. Then, OSubnet resources would be created within that VPC, allocating specific IP ranges for public and private use. You typically deploy these across multiple availability zones for high availability, e.g., 2 public, 2 private subnets. Internet Gateway and Route tables. An OS Internet Gateway resource would be attached to the VPC. OS routeable resources would be created to ensure the public subnets route internet-bound traffic through the IGW, while private subnets route their traffic through a NAT gateway, if needed for outbound internet access from private subnets, or primarily keep traffic internal. Security and load balancing. Security groups define separate security group resources for your web servers, allowing inbound HTTP/HTTPS from the ALB. For your database, allowing inbound traffic only from the web server security group, and for the ALB itself, allowing inbound HTTP/HTTPS from the internet. Application Load Balancer, ALB. An OSLB resource would be created, specifically an ALB, deployed into your public subnets. An OSLB listener would be configured to listen on ports 8443 and forward traffic to a target group. Target group. An OSLB target group would be defined, representing the group of EC2 instances behind the ALB. Compute and database, EC2 instances. OS instance resources would be created for your web servers, placed in the private subnets. They would be associated with the web server security group and registered with the ALB's target group via OSLB target group attachment. You might use count or forEtch to provision multiple instances. RDS database. An OSP instance resource would be created for your database, placed in private subnets via DB subnet group name, and associated with the database security group. Interdependencies. Terraform ensures this layered setup works. The VPC must exist before subnets. Subnets and security groups must exist before EC2 instances, or the database can be provisioned within them. The ALB needs a target group and instances to forward traffic to. This declarative approach, defining the desired end state, allows Terraform to resolve the necessary order automatically. Troubleshooting common Terraform issues. Even with best practices, you'll encounter situations where Terraform doesn't behave as expected. Here are common issues and effective troubleshooting strategies. Syntax errors in your configuration. Symptom, error, invalid block type argument, error, unsupported argument, error, argument not used. Diagnosis. Terraform provides clear error messages indicating the file, line number, and often the nature of the syntax error. Solution. Use Terraform Validate. This command checks your configuration for syntax validity and internal consistency without touching any cloud resources. Pay close attention to the error messages, correct typos, ensure correct block nesting, and verify argument names against provider documentation. State drift. Symptom. Terraform plan shows unexpected changes, plus, even if you haven't recently modified your Terraform code, or warns about resource not found. This means the actual cloud infrastructure has diverged from Terraform's state file. This can happen if resources were manually modified or deleted in the Cloud Console CLI, or if another process changed them. Diagnosis. Run Terraform plan. The output will precisely detail the detected differences between your state file and the cloud. Solution. If the drift is intentional, update your Terraform configuration to match the new desired state, then run Terraform apply. If the drift is unintentional, e.g., someone accidentally deleted a resource, consult your team. If the change needs to be reverted, run Terraform apply, which will attempt to restore the resources to the state defined in your code. Run Terraform apply refresh, only to update the state file to reflect current cloud reality without applying any configuration changes. This synchronizes Terraform's memory without modifying infrastructure. Provider errors, authentication, permissions, rate limiting. Symptom, error launching source instance, unauthorized operation permissions, error, request limit exceeded rate limiting, error, invalid client tokened authentication. These errors come directly from the cloud provider's API. Diagnosis, permissions. For Oz, check CloudTrail logs in your AWS account. They log every API call and whether it succeeded or failed due to permissions. The error message usually specifies the API action, EC2, run instances, S3, create bucket that was unauthorized. Ensure the IAM user role Terraform is using has the necessary permissions. Authentication. Verify your Oz credentials, access key ID, secret access key are correctly configured and valid. Check the /Oz/credentials file or environment variables. Rate limiting. Cloud providers have API rate limits. If you're creating many resources concurrently or have a very large configuration, you might hit these. Terraform generally handles retries, but persistent issues might require reducing parallelism or seeking limit increases from the cloud provider. Solution: adjust IAM policies, verify credentials, or simplify your deployment for rate limit issues. Dependencies issues. Symptom: resources fail to create because a dependency, like a security group or subnet, isn't ready or Terraform tries to destroy a resource that's still in use. Diagnosis: Terraform generally handles implicit dependencies well. If a resource fails, check its error message to see what it's waiting for. Occasionally, you might need to add an explicit dependency meta-argument, as discussed in Chapter 7, but this is rare and should be considered a workaround for unclear dependency chains. Solution: ensure all necessary components exist and are correctly referenced. Verify the correct resource IDs are passed. Network connectivity problems. Symptom: EC2 instances aren't reachable, web servers don't respond, services can't communicate. Diagnosis: this is often a security group or network ACL misconfiguration. Check OSSecurity group and OSNetworkECL resources. Are the ingress, inbound, and egress, outbound rules correct? Are ports open? Is the source destination CIDR correct? Verify OSRouteable configurations. Are routes correctly pointing to the Internet Gateway, NAT Gateway, or VPC peering connections? Check subnet associations for resources. Solution: review your network configuration in Terraform. Use the Terraform state show command to inspect provisioned security group IDs and then verify their rules in the Cloud Console. Temporarily relaxing rules for testing and immediately reverting can help identify the culprit. Debugging strategies. Read error messages carefully. They are your first and best line of defense. Use Terraform plan intelligently. Always run it before apply. Pay attention to the plus, tilde, symbols and the detailed attribute changes. TFLOG environment variable. For very verbose logging, set the environment variable tflog equals trace before running any Terraform command, e.g., tflog equals trace Terraform apply. This will print extensive debug information from Terraform core and providers, helping pinpoint where an operation is failing at a low level. Official documentation. The Terraform registry for specific providers and resources is invaluable. It details all arguments, attributes, and common usage patterns. Cloud provider documentation, AWS docs, Azure docs, GCP docs, explains the underlying service behavior. Community support. HashiCorp's official Discuss forums, Stack Overflow, and various online communities are excellent resources for finding solutions to common or unique problems. Provide clear details of your configuration and the error messages. Check cloud provider logs and dashboards. Use AWS CloudWatch logs, CloudTrail, or the equivalent services in your cloud provider to get deeper insights into why a service API call might be failing. Handling infrastructure changes and refactoring. Terraform is designed to manage infrastructure over its entire lifecycle. Minor updates. If you change an argument in a resource, e.g., updating an EC2 instance type, Terraform plan will show a modify or plus, replace, destroy and recreate operation. Terraform apply will then make that change. Terraform itself determines whether a change can be applied in place or requires recreation. Major refactors and renames. If you rename a resource's local name in your TF files, e.g., resource ausinstance, old name to resource ausinstance, new name, Terraform will see old name as needing to be destroyed and new name as needing to be created. This is usually not what you want for an existing resource. To prevent this, use Terraform state mv old address new address. This command updates the state file to reflect the new logical name without touching the actual cloud resource. For example, Terraform state mv ausinstance old name ausinstance new name. This is critical during major refactorings, moving resources into modules, or reorganizing your configuration across files. Planning for deprecations and migrations. Stay informed about changes in cloud provider services and Terraform provider versions. When resources are deprecated or removed, plan a migration path. The ability to version control your infrastructure code makes these transitions more manageable. Recap and further reading. Moving from individual resource definitions to orchestrating full application environments is where the true power of Terraform becomes apparent. The static website and web application scenarios demonstrate how different cloud services combine to form complete solutions, all managed through declarative code. While this power is immense, troubleshooting is an inevitable part of the journey. By understanding common issues, interpreting error messages, and using the right debugging tools, you can confidently address the challenges that arise. The iterative process of defining, deploying, validating, and troubleshooting infrastructure is key to successfully operating in the cloud-native world. For more detailed deployment, best practices, and validated architectures, explore case studies and solution architectures from Oz, Azure, or GCP directly. For in-depth troubleshooting guides direct from HashiCorp, refer to the troubleshooting section within the official Terraform documentation. For highly specific resource-level troubleshooting, always consult the relevant provider documentation on the Terraform registry, as it often includes notes on common errors or unique behaviors. Chapter 11. Best Practices, Testing, and Advanced Management. Introduction, Elevating Your Terraform Game. You've learned the core tenets of infrastructure as code, mastered Terraform syntax, and explored how to provision and manage cloud resources. You've even begun to automate deployments through CI/CD and troubleshoot common pitfalls. As you gain more experience, you'll inevitably encounter situations where just making it work isn't enough. For production environments, large teams, or complex architectures, you need to think about long-term maintainability, reliability, and cost-effectiveness. This chapter focuses on elevating your Terraform skills by diving into crucial best practices, various testing methodologies, and briefly touching on advanced management tools that complement Terraform. Adopting these discipline approaches will transform your configurations from functional scripts into robust, scalable, and resilient infrastructure blueprints. Terraform best practices. Writing maintainable and scalable code. Good Terraform code, like good software code, is readable, reliable, and easy to maintain. Code structure and organization, modularization. As discussed in Chapter 6, break down your infrastructure into logical, reusable modules. Don't put everything in the root module. Common modules include VPC, Ect2Instance, Auto-Scaling Group, RDS Database, etc. This improves readability, reusability, and reduces duplication. Environments folders. For managing distinct environments, dev, staging, prod, use separate top-level directories named environments/dev, environment staging, environments prod. Each directory contains its own root Terraform configuration, inputs e.g. Terraform tfvars, and manages its own state file via a remote backend. This explicit separation is often clearer and more robust than relying solely on Terraform workspaces for significantly divergent environments. File organization. Within each module or root configuration, keep files organized. Main.tf contains the primary resource definitions. Variables.tf contains all input variable declarations. Outputs.tf contains all output declarations. Versions.tf explicitly defines required Terraform and provider versions. Providers.tf, if separate from versions, TF defines provider configurations. Locals.tf contains all local value definitions. Naming conventions. Adopt consistent and descriptive naming conventions for everything. Local names. For resources, e.g. ausinstance web server, variables, e.g. instance type, and outputs, e.g. web endpointer. Use snake case. Cloud resource names. Use tags, e.g. name tag in AWS, to give meaningful, human-readable names to your actual cloud resources. Often, these names incorporate an environment prefix, e.g. devwebserver01, proddbmain. Parameterize. Leverage locals and input variables to construct names dynamically and consistently across your resources and environments. Documentation. Within code comments. Use for single-line comments or for multi-line blocks to explain complex logic, design decisions, or non-obvious configurations. README files. Every module and every root environment configuration should have a comprehensive README file. This is crucial for onboarding new team members and for future reference. It should include purpose of the module environment, usage instructions, how to deploy, list of inputs with their descriptions, types, and defaults, list of outputs with their descriptions, dependencies, e.g. specific OS permissions required. Examples: input-output descriptions. As always, provide clear description attributes for all variable and output blocks. Version pinning. Always pin your Terraform CLI version and your provider versions, using required version and required providers blocks. This prevents unexpected behavior due to breaking changes in newer versions and ensures consistent deployments across different environments or team members. Use optimistic constraints where appropriate, e.g., 5.0 for providers, 1.0.0 for Terraform CLI. Small, incremental changes. Avoid monolithic changes. Break down large deployments or refactors into smaller, manageable, and reviewable pull requests. This reduces the blast radius of errors and makes troubleshooting easier. Always run Terraform plan to understand the full impact of your changes before Terraform apply. Principle of least privilege. Define the minimum necessary IAM permissions for the user role executing Terraform, as well as for the resources Terraform provisions. This reduces the risk of accidental damage or security breaches. Regularly audit your IAM policies. Testing your Terraform configurations. Treating infrastructure as code means it deserves the same rigorous testing as application code. Effective testing helps catch errors early, prevents regressions, and builds confidence in your deployments. Static analysis, pre-deployment checks. These tests don't interact with your cloud provider. They analyze your code pre-deployment. Terraform validate. Essential, always run first. Checks configuration syntax and internal consistency. Terraform FMT ensures your code adheres to standard Terraform formatting. Integrates well into CI/CD pipelines. Linting, e.g., tflint. a static analysis tool that checks for potential errors and warns about best practices, style conventions, and even some security vulnerabilities, e.g., using 0.0.0.0/0 in security groups. Security scanning, e.g., Checkov, Terraform, TFSec. These tools scan your Terraform code for common security misconfigurations and policy violations before deployment. They enable shift-left security, policy as code, e.g., HashiCorp Sentinel, Open Policy Agent OPA. These frameworks allow you to define custom organizational policies and enforce them at the plan stage. Examples: no public S3 buckets. All resources must have a cost center tag. Only approved instance types allowed. Unit testing, module level, mostly conceptual. While less common than in application development due to Terraform's declarative nature, some tools allow for unit-like testing of modules. This often involves programmatically applying a module with dummy inputs and asserting internal resource properties or outputs. Terraform Go-based. A popular Go library by Gruntwork that allows you to write automated tests that deploy real infrastructure in a temporary environment using your Terraform code. Run assertions against the deployed resources, e.g., check that an S3 bucket exists or that an EC2 instance is running. Clean up the resources afterwards. This is closer to integration testing, but can be used for testing individual modules. Integration testing. This is where your Terraform code is actually deployed to a temporary, isolated cloud environment, and then assertions are run against the live infrastructure. This is the most robust form of testing for Terraform. Workflow. Provision an isolated test environment, e.g., a dedicated AWS account or a new VPC. Apply your Terraform configuration to this environment. Run automated tests that verify the functionality and correctness of the deployed infrastructure, e.g., can I SSH into the server? Is the web application accessible? Is the database configured correctly? Destroy the test environment to clean up resources and avoid lingering costs. Tools. Terraform is very well suited for this. You can also use other testing frameworks, e.g., Python's Unitest, Ruby's RSpec, combined with Cloud SDKs, Bodo 3 for Oz, to interact with the deployed resources. Cost estimation, e.g., InfraCost. While not strictly testing, tools like InfraCost integrate into your CI/CD pipeline and analyze your Terraform plan output to provide a cost estimate of the changes. This is invaluable feedback, especially for larger deployments, helping to prevent unexpected cloud bills. Advanced management tools and complementary technologies. Terraform is a powerful orchestrator, but it exists within a broader ecosystem of tools that can enhance its capabilities. Terraform Cloud Enterprise. Reiterated from Chapter 9, HashiCorp's managed service offering for Terraform. Provides cloud-based remote state, remote plan apply execution, team management, private module registry, and policy as code, Sentinel. For serious adoption in larger organizations, these platforms greatly streamline Terraform operations. TerraGrunt. A thin wrapper around Terraform that provides extra tools for keeping your configurations dry, don't repeat yourself, managing remote state, and orchestrating multiple Terraform modules across different environments. It's particularly useful for structuring multi-environment, multi-module deployments. Other ISC tools, brief comparison for context. CloudFormation, AWS, ARM Templates, Azure, Deployment Manager, GCP. Cloud-specific declarative ISC tools. Offer deep integration with their respective clouds but lack multi-cloud capabilities. Pulumi uses general-purpose programming languages, Python, JavaScript, Go, C#, to define infrastructure. Appeals to developers more comfortable with traditional programming. Multi-cloud. Ansible, Chef, Puppet. Configuration management tools primarily focused on installed software and operating system configurations on top of provisioned infrastructure. They often complement Terraform, with Terraform provisioning the VMS and networks, and Ansible configuring the applications running on them. Crossplane. An open-source Kubernetes add-on that allows you to provision and manage cloud infrastructure from your Kubernetes cluster, treating external resources as extensions of the Kubernetes API. Recap and further reading. Moving beyond basic resource provisioning requires a commitment to best practices, robust testing, and awareness of complementary tools. By adopting consistent code structure, thorough documentation, strict version pinning, and a security-first approach, you build maintainable and scalable Terraform configurations. Integrating static analysis, unit, and integration tests into your CI/CD pipeline ensures reliability and catches errors early. Leveraging advanced management platforms like Terraform Cloud or wrappers like TerraGrunt can further streamline operations for complex, large-scale environments. The journey with Terraform is continuous. Embrace these practices to become a true infrastructure as code master. For detailed guides on specific static analysis tools, search for tflint, tfsec, Chekhov documentation. For in-depth tutorials on Terratist, explore Gruntworks' comprehensive guides and examples. To dive deeper into TerraGrunt, refer to its official documentation and learning resources. Stay updated. Follow the official HashiCorp blog, attend relevant conferences, HashiConf, and engage with the Terraform community to stay abreast of new features, best practices, and emerging tools. Chapter 12. Beyond the Basics. Next steps for your Terraform journey. Introduction. The unfolding landscape of infrastructure as code. Congratulations! You've journeyed through the fundamentals of infrastructure as code and gained a significant understanding of Terraform. From its core principles and basic command workflow to mastering modules, managing state, implementing security best practices, and integrating with CI/CD pipelines, you now possess a comprehensive toolkit to declare, provision, and manage your cloud infrastructure with confidence. However, the world of cloud computing and ISC is dynamic and ever-evolving. This final chapter serves as a roadmap for your continued learning, offering insights into advanced concepts, opportunities for community contribution, and a look at the exciting future of infrastructure automation. Your journey with Terraform doesn't end here. It merely begins a new phase of exploration and mastery. Advanced cloud architectures, applying Terraform to complex scenarios. As you gain experience, you'll encounter more complex cloud architectures that build upon the foundational concepts we've covered. Terraform is perfectly suited for these challenges. Multi-region and disaster recovery, Doctor. Deploying infrastructure across multiple Oz regions to ensure high availability and business continuity in case of a regional outage. Terraform can manage resource replication, cross-region networking, and Doctor orchestration for services like databases and storage. Complex networking. Implementing sophisticated network designs, including VPC peering, transit gateways for many-to-many VPC connectivity, direct connect for hybrid cloud solutions, and advanced routing configurations. Serverless architectures. Provisioning serverless components like AWS Lambda functions, API gateway, DynamoDB tables, and SQS queues. Terraform helps define the entire serverless application stack, including permissions and event triggers. Container orchestration, Kubernetes. While Kubernetes often manages its own resources, Terraform is commonly used to provision the underlying Kubernetes cluster itself, e.g., AWS Elastic Kubernetes Service, EKS, clusters, Azure Kubernetes Service, AKS, Google Kubernetes Engine, GKE. You can then use Kubernetes native tools or other Terraform providers, like the Kubernetes provider, to manage resources inside the cluster. Hybrid cloud and on-premises integration. Managing resources that span both public cloud providers and your on-premises data centers, leveraging VPNs, Direct Connect, and specialized Terraform providers for VMware, OpenStack, or other private cloud technologies. Contributing to the Terraform ecosystem. Terraform's power comes in part from its vibrant open-source community. As you deepen your knowledge, consider contributing back open-source modules. Develop and share your own battle-tested Terraform modules on the Terraform registry or GitHub. This allows others to benefit from your patterns and helps you refine your designs through community feedback. Provider development, conceptual. If you work with a unique API or a service that doesn't have a Terraform provider, you can learn to write your own custom provider. This is an advanced topic requiring Go programming knowledge, but it allows you to extend Terraform's reach to virtually any service. Documentation and examples. Improve existing documentation, contribute new examples, or write blog posts about your experiences and solutions. The community thrives on shared knowledge. Bug reports and feature requests. Actively participate in the official Terraform GitHub repositories by reporting bugs, suggesting new features, or contributing code fixes. Staying current with Terraform and its ecosystem. The cloud and ISC landscape evolves rapidly. To remain proficient, cultivate habits of continuous learning. Official HashiCorp resources. HashiCorp blog. Regular updates on new features, releases, and best practices for Terraform and other HashiCorp products. HashiCorp Learn. Continuously updated tutorials and guided learning paths for new features and advanced topics. Terraform release notes. Essential for understanding new capabilities, bug fixes, and breaking changes in each release. Community engagement. Terraform Discuss forums. A great place to ask questions, share knowledge, and learn from others' challenges. Industry blogs and newsletters. Follow prominent cloud engineering, DevOps, and ISC thought leaders and publications. Online courses and certifications. Numerous platforms offer advanced courses. Professional development and certifications. Formal certifications can validate your expertise and boost your career. HashiCorp offers a dedicated certification. HashiCorp Certified, Terraform Associate. This certification validates your foundational understanding of ISC concepts and Terraform's core functionalities. It's an excellent next step to demonstrate your proficiency. Cloud Provider Certifications. Complementing your Terraform skills with cloud-specific certifications, e.g., AWS Certified Solutions Architect, Azure Administrator Associate, is highly recommended. These validate your in-depth knowledge of the underlying cloud services Terraform provision. The future of infrastructure as code. The journey of ISC is far from over. Expect to see continued advancements in several areas. Increased abstraction and higher-level constructs. Tools will continue to emerge that abstract away more low-level infrastructure details, allowing teams to define desired outcomes rather than individual components. Projects like Crossplane managing cloud resources directly from Kubernetes are early examples. Autonomous infrastructure. The long-term vision is towards self-healing and self-optimizing infrastructure, where AI/ML analyze patterns and automatically adjust resources to meet performance and cost goals, with ISC providing the declarative baseline. Shift-left security and policy enforcement. More sophisticated policy as code tools will provide even stronger guardrails, ensuring that security, compliance, and cost policies are enforced throughout the entire infrastructure lifecycle, preventing non-compliant deployments altogether. Environmental sustainability in ISC. As awareness around cloud environmental impact grows, ISC tools might integrate metrics and optimizations for carbon footprint and energy efficiency. Broader ecosystem integration. Continued integration between ISC tools, configuration management, monitoring, and compliance platforms, leading to a more unified and intelligent infrastructure management landscape. Concluding thoughts, the power you now hold. You've embarked on a journey that fundamentally transforms how you interact with cloud infrastructure. By adopting infrastructure as code with Terraform, you gain immense power. The power to provision complex environments with unmatched speed and reliability. The power to collaborate effectively, eliminating costly manual errors and inconsistencies. The power to treat your infrastructure with the same diligence, version control, and automation as your application code. The power to adapt quickly to changing business needs and scale your operations with confidence. The skills you've acquired in this book are not just about a single tool. They represent a modern, essential approach to managing digital infrastructure. Embrace continuous learning, explore new challenges, and contribute to the vibrant community. The cloud is your canvas, and Terraform is your blueprint for building the future. Glossary of key terms. Apply, Terraform apply. The command that executes the changes proposed in a Terraform plan, provisioning or modifying resources in the cloud. Backend, where Terraform stores its state file, can be local default or remote, e.g. S3, Terraform Cloud. CI/CD, continuous integration, continuous delivery. automated processes to build, test, and deploy code, including infrastructure code, frequently and reliably. Cloud agnostic, designed to work across multiple cloud providers, e.g., AWS, Azure, GCP, not specific to one. Configuration drift, when the actual state of infrastructure deviates from its intended state as defined in code, often due to manual changes. Declarative, describes the desired end state of the infrastructure, what you want, leaving the tool to figure out the steps to achieve it. How? Depends in, a meta-argument used to explicitly define a dependency between resources when Terraform cannot infer it automatically. Destroy, Terraform destroy, the command that tears down all resources managed by a Terraform configuration. Dynamic block, a way to generate repetitive nested configuration blocks within a resource definition based on iteration over a list or map. For each, a meta-argument used to create multiple instances of a resource or module based on elements in a collection, map, or set, allowing distinct configurations for each. Function, built-in operations in Terraform HCL to transform or manipulate data, e.g., join, length, JSON encode. HCL, HashiCorp configuration language, the native declarative language used by Terraform to define infrastructure. ISC, infrastructure as code, managing and provisioning infrastructure using machine-readable definition files, enabling version control, automation, and consistent deployments. IAM, identity and access management, a service that helps you securely control access to cloud resources. Idempotence, the property that applying the same operation multiple times produces the same result without unintended side effects. Implicit dependency, when Terraform automatically infers that one resource must be created before another because its attributes are referenced. Init, Terraform init, initializes a Terraform working directory, downloading necessary provider plugins, and configuring the backend. Input variable, a parameter that allows you to customize a Terraform configuration without directly editing its resource definitions. Lambda, AWS Lambda, AWS serverless compute service, allowing you to run code without provisioning or managing servers. Lifecycle, a meta-argument that allows customizing Terraform's default behavior when managing resources, e.g., prevent destroy. Local value, a named expression within a Terraform configuration used to simplify complex calculations or avoid repetition. Count, a meta-argument used to create multiple instances of a resource or module based on a numerical count. Module, a reusable, self-contained package of Terraform configurations that deploys a specific piece of infrastructure. Output value, an exported attribute of a Terraform configuration or module that can be displayed to the user or consumed by other configurations. Plan, Terraform plan, generates an execution plan showing what changes Terraform will make to infrastructure before actually applying them. Policy as code, defining security, compliance, or cost policies as code, which can be enforced automatically during the ISC workflow. Provider, a plugin that allows Terraform to interact with a specific cloud platform, SaaS, or API. Resource, a block in Terraform configuration that declares an infrastructure component, e.g., an S3 bucket, an EC2 instance. S3, simple storage service, AWS object storage service, often used for static website hosting, backups, and data lakes. Security group, a virtual firewall that controls inbound and outbound traffic for individual cloud resources. Sensitive data, information that should be protected, such as passwords, API keys, or private keys. State file, Terraform TF state, Terraform's record of the real-world infrastructure it manages, mapping resources in the configuration to their actual deployed counterparts. State locking, a mechanism, usually provided by remote backends, that prevents multiple concurrent operations from corrupting the state file. VPC, Virtual Private Cloud, a private, isolated section of the cloud where you can launch resources. Workspace, a feature in Terraform that allows managing multiple, distinct instances of the same configuration, each with its own isolated state file. Recommended resources for continued learning. HashiCorp Learn, learn.hashicorp.com, official tutorials, concepts, and detailed guides. Terraform registry documentation. Registry.terraform.io, comprehensive documentation for providers and modules. AWS documentation, or your chosen cloud provider. docs.oz.amazon.com, in-depth information on the underlying cloud services. The Terraform Community Forum. Discuss.hashicorp.com, engage with other practitioners, ask questions, share knowledge. Terraform GitHub repositories. Explore the source code, open issues, and contribute. Specific books. Terraform, Up and Running by Yevgeny Brickman, O'Reilly. Cloud Native DevOps with Kubernetes by J.B. Rainsberger et al., O'Reilly. Online course platforms. Coursera, Udemy, A Cloud Guru, Pluralsight search for advanced Terraform courses. Industry blogs. Follow blogs from HashiCorp, Gruntwork, Cloudcraft.co, and prominent DevOps and cloud engineers on Medium, Devdo, or LinkedIn.